Among the thousands of lifeless planets, it is impossible to find one as picturesque and full of life as Earth, which seems to defy the very laws of the cosmos. All life that has appeared on this planet owes its existence to water. The first complex molecules, the first organisms, the first human beings. They all have their roots in water. But how did so much liquid water appear on Earth, among so many desert planets? For all of science, the origin of water remains a mystery. Whether the water originated in the infernal entrails of the young Earth or millions of light years away in the inaccessible depths of space is a puzzling question for scientists. The closer we get to the solution, the closer we will be to answering the question, are we alone? Today we will try to find the sources of water and life on our planet, diving into the beginnings of the solar system and discovering why water chose Earth, saving it from the fate of Mars and Venus. Approximately 77% of the surface of the Earth is covered by water. The imposing amount of water on the planet seems quite normal to us, and according to what we know about the birth of planets, the Earth should have been completely dry. Let's go back to the beginning of our solar system's life. We are facing a young sun that has just formed from the remains of an ancient supernova that left a gigantic cloud around it, a protoplanetary disk of dust and gas that stretched for hundreds of millions of kilometers due to the star's nuclear processes. Many of the planets we know today, including Earth, will form from these building blocks in billions of years, since the only materials that could exist around the sun at that time were stone and iron. The four closest planets were formed from them. According to a recent study by the California Institute of Technology, the planetesimals from which Earth was formed were composed of dry, rocky materials. These construction materials did not contain volatile substances, such as water. In particular, the gas was not available in the early stages, since it was mostly expelled beyond the orbit of Mars, so it was impossible for there to be an atmosphere. But, wait a moment, what does the atmosphere have to do with this? In its beginnings, the Earth did not have a moderate temperature like the current one. The disk was very hot and the sun was very active, so, instead of water, seas of magma spilled over the planet under deadly ultraviolet radiation. Therefore, there was no way that water could be retained in liquid form on such a hot Earth, and, in the absence of an atmosphere, water could not accumulate as vapor. The magmatic period may have lasted several tens of millions of years until the surface cooled, and, according to many studies, including those of the University of Chicago, water began to appear after that. But how did this happen? The Earth was not formed with an ocean, since it would have boiled due to the heat of the protoplanet and would have become a dry and burned planet like Venus, for example. Instead, water spilled inside it, which created the conditions for the emergence of all life that exists today. So, how could water reach the dry Earth? Perhaps the answer to this mysterious question is right above us. Water could have been brought to Earth by extraterrestrial messengers traveling through space. We're not talking about alien life forms, but about common comets and asteroids. In a revolutionary study by scientists using NASA's Stratospheric Observatory for Infrared Astronomy, SOFIA, water was detected for the first time on the surface of the asteroid Bennu. The presence of water molecules in the rocks of Bennu indicates that such asteroids could have brought water to Earth in the early solar system. The discovery was possible thanks to SOFIA's unique capabilities, which include a powerful telescope mounted on a Boeing 747 SP aircraft, flying over more than 99% of the water vapor in Earth's atmosphere. SOFIA was able to capture infrared waves that would otherwise have been blocked, allowing previous observations of the composition of Bennu's surface. Comets are composed of frozen gases, rocks, and dust, and orbit the sun in highly deformed elliptical orbits. They are actually snowballs that carry a lot of water and other building materials, such as methane, ammonia, and carbon dioxide. As they approach the sun, comets melt and release clouds of water vapor that are captured by the Earth's gravity. Asteroids are the remains of the primeval solar system during its active formation. They also had a significant impact on filling the Earth with various important elements, such as silicate rocks, iron, nickel, etc., depending on their compositional class. For example, the most common critical, or Class C, asteroids have up to 135% water in their composition, whose molecules could be transported as space dust. Therefore, it seems very likely that comets and asteroids may be behind the global appearance of water on Earth. The carbonaceous asteroid Bennu is considered a time capsule of the early solar system, containing valuable clues about its formation and evolution. The discovery of water in Bennu adds to the growing body of evidence indicating that carbonaceous asteroids may be important sources of water and organic compounds essential to life. The presence of hydrated materials in Bennu, which are formed in the presence of water, suggests that Bennu's parent body had liquid water in the past. This also means that Bennu or similar asteroids could have been carriers of water to the early Earth, contributing to the formation of the planet's initial water supply. Particularly in the period between 38 and 4 billion years ago, the inner planets of the solar system suffered a heavy bombardment of asteroids and comets, better known as the Late Heavy Bombardment. This event could explain the abundance of water on the planet, but still requires in-depth investigation, such as the craters on the Moon, which were probably left by the bombardment. The atmosphere was also not an obstacle for these travelers, so asteroids and comets freely entered terrestrial space, accumulating the first water. According to research by space chemists led by Nicholas Dofas, about 10% of the water could have been brought to Earth by comets and asteroids. Along with asteroids and comets, meteorites are another candidate. Meteorites are fragments of asteroids or comets. The most likely source of water could be molten meteorites that have been floating since the solar system's formation. However, recent studies of this type of meteorites have shown that they have a very low water content, but not everything is lost in meteorites. There are several other types, including carbonates and entities. Despite their complicated names, these two species are currently considered the most probable source of water on Earth, since they contain up to an average of and could even bring 3 times more water to Earth than our oceans have now. Over time, as the Earth cooled and geological activity decreased, the first steps were taken toward the development of plate tectonics. The movement of these plates formed new mountains and oceanic trenches, which contributed to the transfer of water from rivers to oceans. Plate tectonics also allowed water to be stored in the evolving mantle of the Earth, which motivated geological activity and, therefore, the formation of water on the planet. The constant bombardment of cosmic bodies also continues to fill the Earth with water, so water arrived on Earth almost continuously, gradually covering its revitalized surface. The Earth, still young and just beginning its active internal formation, approximately between 2.5 and 4 billion years ago, did not have enough opportunities to drain water toward the mantle, for example, due to its limited capacity. Therefore, the combined efforts of asteroids, comets, and internal activity could have completely covered our Earth with water, turning it into a completely aquatic world without any land. In 2021, scientists from the Universidad de Harvard, led by Junji Dong, carried out a geochemical study of the planet's water reserves and, surprisingly, discovered that the original ocean of the Earth could have been between 1 and 2 times larger than the current one. According to Junji Dong, this ocean could have flooded between 70 and 90% of the first continents. A group of scientists calculated and compared the approximate amount of water with the surface of the current land surface and arrived at the conclusion that the original ocean of the Earth could have been between 1 and 2 times larger than the current one. According to Junji Dong, this ocean could have flooded between 70 and 90% of the first continents. A group of scientists calculated and compared the approximate amount of water in the current mantle and billions of years ago, and discovered that the ancient mantle could not contain as much water as it does now. This means that the residual water would have had to be stored on the Earth's surface. This theory could completely change our understanding of how the early Earth developed, and, in particular, all life. Current theories about the origin of living organisms in shallow pools with a mixture of different minerals and building blocks on land or in hydrothermal vents at the bottom of the ocean are very popular. However, the global ocean could overturn these hypotheses, which would require new explanations about how life arose or a revision of what we know about the conditions for its formation. For example, scientists are already raising the first theories about where organisms evolved. Thomas Carroll believes that the protected pockets of water in the oceanic rocks could be the answer to this question. However, if the Earth had remained an aquatic world, the continents and life forms that we know would never have formed. The delicate balance between the water brought by asteroids and comets and the tectonics of the Earth has made the planet ideal for life. If there had been too much water or too little, Juni Dong states that nothing would have worked, but only extraterrestrial space bodies could not form and maintain an ocean for a long time. Venus and Mars also suffered bombardments, but failed to retain much water on their surfaces for a long list of reasons, and one of them is the location and temperature regime in the solar system. While Venus is too close to the Sun and Mars is too far away, the Earth seems to be in an ideal place to keep water in a liquid state instead of gaseous or solid. This place in planetary systems is called the Goldilocks zone. This zone, which is the most suitable for the appearance of life, differs in each system depending on the type of star. For us, it exists between 0.99 and 17 Australian dollars, right on the edge of the zone. Without the Goldilocks zone, the water that reaches us through external routes would evaporate or turn into ice. In addition, the ideal zone maintains the water cycle, regulating weather and climate, and balances the functioning of ecosystems. The Goldilocks zone played an equally important role in the formation of the Earth as a habitable planet, since it supports and stores water and all the additional elements brought from outside and formed within the Earth itself. All the previous theories and assumptions require careful and serious investigation to finally establish the complete history of the origin of water. The recent discovery on Bennu underscores the importance of continuing research to understand the origin of water on Earth. This research not only supports existing theories, but also provides new insights and evidence that deepen our knowledge of the early solar system and potential water sources. Missions such as that of OSIRIS-REx, which collected samples from the surface of Bennu with the aim of returning them to Earth for detailed laboratory analysis, will provide unprecedented information on the mineralogical and chemical properties of Bennu, further elucidating its role in the history of the solar system. However, investigating this question is not an easy task at all. First, the water that is of most interest to scientists is hidden in the depths of the subsoil under the oceans. This water is likely to have a different composition than seawater, so it would be possible to find out exactly what the main sources of water were. Therefore, scientists are likely currently using an incorrect ratio of DH, deuterium, and hydrogen for the Earth, which is the main method for comparing the chemical composition of the Earth and other cosmic bodies. However, it is extremely difficult to reach the mantle, although scientists have already had some successes in this direction, having first drilled a mile under the bottom of the Atlantic Ocean, where they recovered the first fragments of the mantle, but they are still far from carrying out complete and high-quality studies on water. Despite this, the difficulty is further complicated by the insufficiency of samples of comets and asteroids to study the correlation between their chemical composition and the water masses of the Earth. The planetary protodisk around the Sun, as it moves away from it, has a completely different ratio of deuterium and hydrogen in its composition. The planetary disk around the Sun, as it moves away from it, has a completely different ratio of deuterium and hydrogen in its composition. So, it is difficult to determine where the space body that brought the water could have formed to better understand its composition and amount of water. In addition, the diversity of water sources requires a multifaceted study to determine the contribution of each group of objects. To solve this problem, it is only necessary to study several space bodies at different distances to determine which population of space bodies is responsible for the water on the planet. But today's scientists can only measure the closest and brightest objects. The water of the Earth itself can also confuse the trail due to changes in its composition over millions of years. The search for what filled the Earth with water will take a long time, but gradual improvements in analytical methods and future research missions will one day shed light on the sources of our life including our own. Scientists continue to work in the hope of advancing our understanding of how water arrived in the solar system in 2021. Music, type of meteorite called instatite chondrite. The isotopic composition of this meteorite is similar to Earth's and is probably a remnant of planetary material from the outer solar system. According to the study, these meteorites could have brought 3 times more water than our oceans now contain. In addition, the hydrogen and nitrogen isotopes of the chondrules match those found in the mantle, indicating that most of the air in the atmosphere could come from these rocks. However, the composition of seawater does not fully match that of meteorite water. It is possible that other space bodies mixed with the water, changing its original chemical content and confusing scientists. On the other hand, a scientist group was led by Edward D. Young has developed a completely unexpected theory that could displace space objects from first place as major sources of water on Earth. Most of the water could have appeared on the planet from ancient magma oceans, where oxygen interacted with hydrogen in the early atmosphere. The interaction of magma and hydrogen produces water. This process does not deny the impact of asteroids, comets, and meteorites, but adds to the history of water on Earth. Finally, in June 2023, another surprising theory emerged that goes against what we know about Earth's formation. According to this theory, instead of water appearing on Earth due to cosmic bodies, our planet was mainly attracted by pebbles and ice particles from the protoplanetary disk in the early stages of its existence, like a vacuum cleaner. So the presence of water does not depend on a random event such as the bombardment of comets, according to the main author, Isaac Onet, and therefore, the Earth could have formed in as little as 3 million years instead of hundreds of millions of years. This theory could change everything we know about the formation of planetary systems and the origin of water, so more careful research is needed for it to have an even greater impact. Music, the history of water on Earth, is one of the most intriguing questions for modern science. Scientists propose many theories based on assumptions from studies of samples as old as the sun itself, getting closer to the desired solution every day. Whether brought by comets, meteorites, and asteroids, or formed by the Earth itself, water is fascinating for its mystery and its ability to sustain life. And one day, its domain will be dominated, and we will finally know how life arose on Earth. What if the colors we see in the night sky are just the beginning of a story yet to unfold? Our documentary invites you on a journey of discovery, where each chapter unveils the hidden narratives of distant worlds, challenging what we thought we knew about our universe. First, we dive into the blue depths of Neptune, revealing its true colors, a world far beyond our own, where winds howl with ferocity and the skies tell stories of ancient ice and gas. What mysteries does this distant giant hide in its cyan tones? Then we venture to the enigmatic Saturn, where at its north pole, a geometric marvel, the hexagonal storm, defies all explanation. What forces of nature sculpt this strange phenomenon? Can we unravel the secrets of the hexagon? Our odyssey continues as we search for the latest real images of Uranus, this elusive ice giant shrouded in mystery that reveals new truths through modern exploration. What will we discover in the hidden details of its atmosphere and rings? Finally, we travel with Chandrayaan 3 to our celestial neighbor, the Moon. Here, in the silence of the lunar surface, the mission discovers images never seen before by the human eye. What did Chandrayaan 3 witness on the Moon? What secrets are hidden in the dust and craters of our closest companion in space? Join us as we travel the cosmos in search of answers and marvel at the beauty of the universe. This is not just a journey through space. It is an exploration of the unknown, a search for knowledge, and a tribute to the human spirit. The universe is infinite. Welcome to our documentary series, where the mysteries of the universe are revealed before your eyes. Music. In the vastness of our solar system, beyond the asteroid belt and gas giants, lies a world shrouded in mystery. Neptune, the 8th planet from our sun, a distant ice giant, has captured our imagination for decades. We have imagined it as a dark blue sphere on the edge of our cosmic neighborhood, But what if the vision of this distant world was an illusion? This mysterious planet, named after the Roman god of the sea, has hidden its true colors from us, wrapped in a mantle of deep blue. Neptune has been the subject of many stories and scientific investigations, but recent discoveries have eliminated this blue facade, revealing a reality far more complex and fascinating than we could have imagined for years before. Our telescopes have been pointed towards this distant giant, capturing its essence in pixels and data. However, what we saw was not the reality of the planet, but a reflection of our technological and perceptual limitations. The deep blue color that we associated with Neptune was actually the result of our own interpretations, a story that we created and believed without knowing it. Today we invite you to explore Neptune like never before, to delve into its true colors, to understand its atmosphere, and to unravel the secrets of its moons and rings. For centuries, Neptune was represented as a dark blue world, whose color reflected its cold and distant nature in the solar system. This representation, deeply rooted in our collective consciousness, has become a cornerstone of our understanding of this ice giant. But what if this image is a reflection of our perceptions rather than its true appearance? The color of Neptune is a story of scientific evolution and the search for truth. It begins with the Voyager 2 probe, launched by NASA in 1977 and sent to the confines of the solar system, which took the first close-up images of Neptune, painting a picture of the planet bathed in stunning blue. However, these images were not a direct window into the true color of Neptune, but interpretations resulting from processing the data through the lens of human understanding and the technological capabilities of the time. The deep blue color that we saw was the product of improvements made by the scientists to emphasize certain characteristics of the planet. This story began with more advanced telescopes, like the Hubble Space Telescope. These instruments, equipped with cutting-edge technology, allowed astronomers to see the planet's true color. The results of this study were surprising. The new images revealed that the color of Neptune was not the previous intense blue, but a more muted and varied tone. This discovery was not only aesthetic, but a fundamental shift in our understanding of the planet. The reason for this color error lies in how we process and interpret astronomical data. The colors in space images are often enhanced or altered to highlight certain characteristics or make them more distinguishable for the human eye. In the case of Neptune, these improvements over time have led to a collective opinion of its deep blue color. So, what led to this discovery? The key lies in a meticulous study entitled Modeling the Seasonal Cycle of Color and Magnitude of Uranus and Neptune. This study, led by Patrick G.J. Irwin of the University of Oxford, along with a team of experts, set out to unravel the mysteries of the seasonal color changes of Uranus, without and its comparison with Neptune. This study, led by Patrick G.J. Irwin of the University of Oxford, along with a team of experts, set out to unravel the mysteries of the seasonal color changes of Uranus. However, their journey shed light on Neptune's true colors, refuting long-held beliefs. The team carefully analyzed a large amount of data obtained by the L Observatory for 6 decades. This data, complemented by observations from the Hubble Space Telescope, produced a detailed image of Uranus's average color and photometric magnitude, revealing the complex interaction of its seasonal changes. One of the most important aspects of this study was the focus on the reflectivity of Uranus and the abundance of methane. The researchers unraveled a complex relationship between the lower methane content in the polar latitudes and the aerosol particles' different reflectivity. It was thought that this complex interaction of elements in the atmosphere of Uranus was influenced by the presence of methane ice, which added a new layer of complexity to our understanding. In parallel, the study allowed a fascinating comparison with Neptune. Contrary to popular belief, the difference in blue tones between Neptune and Uranus was less pronounced. This discovery was the result of a critical reevaluation of the color of Neptune, which belied the image of deep blue that had taken root in our minds. The methodology used by the team was a combination of quantitative analysis, atmospheric modeling, and advanced spectroscopic observations. They converted the measured reflectance spectra into radians and then to tristimulus values. This process mimicked the planet's visible colors as perceived by the human eye. To bridge the gap between raw data and our visual interpretation, the use of advanced telescopes, such as the Hubble and the Very Large Telescope, played an important role in this endeavor. These technological wonders allowed the team to review and re-examine the true colors of Uranus and, by extension, Neptune with unprecedented precision. As we delve into the mysteries of Neptune, we find ourselves in the midst of a whirlwind of atmospheric activity that contrasts with the relative calm of its stellar neighbor, Uranus. Neptune's atmosphere, a turbulent and dynamic formation, is home to some of the most extreme meteorological phenomena in our solar system. One of the most striking features of Neptune's atmosphere is the presence of colossal storms, the most famous of which is the Great Dark Spot discovered by the Voyager spacecraft in 1989. This enormous storm, similar to Jupiter's Great Red Spot, is a testament to the planet's turbulent nature. A Great Dark Spot, a gigantic rotating storm, offers a window into Neptune's intense atmospheric dynamics. These storms are caused by the strongest winds in the solar system, which reach speeds of is a testament to the turbulent nature of the planet. A Great Dark Spot, a giant rotating storm, offers a window into Neptune's intense atmospheric dynamics. These storms are caused by the strongest winds in the solar system, reaching speeds of up to 1,300 miles per hour. However, the power and magnitude of these winds remain a mystery to scientists, raising questions about their origin and the energy sources that drive them. In contrast, neighboring Uranus is an image of tranquility. Its atmosphere, although composed of hydrogen, helium, and methane, does not present the same violent storms or extreme winds as Neptune. The difference in atmospheric activity between these two ice giants is one of our solar system's many mysteries. Another intriguing aspect of Neptune's atmosphere involves unusual hot spots where temperatures can reach 750 degrees Kelvin. These hot spots represent a paradox, as they exist on a planet so far from the sun. The origin of this heat remains a mystery, but theories suggest it could be caused by internal processes such as auroras or magnetic reconnection in the plasma layers. The origin of these hot spots and Neptune's extreme climatic conditions are the subject of ongoing research. They force us to seek new answers to questions about planetary atmospheres and point to complex internal processes that are not yet understood. As we leave Neptune's turbulent atmosphere, we enter a realm of celestial harmony where the moons and rings revolve around this giant ice giant. By turning our gaze towards Triton, Neptune's largest and most intriguing moon, we discover a world of seasonal changes and atmospheric mysteries. Triton, a unique moon with a retrograde orbit, was the last solid object visited by the Voyager spacecraft during its historic journey through the outer solar system. Due to its retrograde orbit, indicating it was captured by Neptune's gravity, Triton stands out among the moons of our solar system. Its surface, covered in nitrogen ice, is geologically young and active, with dark green stripes indicating the presence of geysers that expel nitrogen gas. Triton's thin atmosphere, whose thickness varies with the seasons, offers a fascinating study of extraterrestrial meteorology. The observations made with the biologically young and active observatory, with dark green stripes indicating the presence of geysers that expel nitrogen gas. The thin atmosphere of Triton, whose thickness varies seasonally, is a fascinating study of extraterrestrial meteorology. The observations made with its great telescope have revealed that the southern hemisphere of Triton is in full summer. This distant moon, despite its distance from the sun, is experiencing significant atmospheric changes. The heat of the summer sun causes the thin layer of nitrogen, methane, and carbon monoxide frozen on the surface of Triton to sublimate and become gas. This process causes the icy atmosphere to thicken as the season progresses on Neptune, whose orbit is 165 times longer than Earth's around the Sun. The season on Triton lasts over 40 years, and the austral summer solstice occurred in 2000. The discovery of carbon monoxide in the atmosphere of Triton, as well as the confirmation of the presence of methane, was a significant advance in our understanding of this moon. The presence of these gases, especially the enrichment of the ice with carbon monoxide in the upper layer of the surface, feeds the atmosphere and determines its seasonal dynamics. These findings required a revision to Triton's climatic and atmospheric models. The complex interaction between nitrogen, methane, and carbon monoxide not only determines atmospheric conditions, but also provides information about the geological and climatic history of the moon. But Triton is not alone. The planet is accompanied by a retinue of smaller moons, each of which contributes to our understanding of this distant world. These moons also show seasonal changes and provide information about gravitational interactions and conditions around Neptune. When we turn our gaze from the moons to the rings of Neptune, we encounter another aspect of the mysterious nature of this planet. Formed by a mixture of dust and ice particles, the rings of Neptune are opaque but fascinating and bear witness to its dynamic history. Scientists believe they are remnants of moons destroyed by collisions or torn apart by Neptune's gravity. The composition and characteristics of these rings are closely related to Neptune's true color and atmospheric phenomena. The subtle tone of the rings, which is affected by the scattering of light in Neptune's atmosphere, adds another layer to the planet's color palette. The rings, reflecting and refracting sunlight, create Neptune's overall appearance as seen from afar. In 2022, the James Webb Telescope captured the sharpest image of this distant planet's rings in 30 years. Photographed with clarity, these rings have changed how we think about this distant planet. The most striking thing about the new Webb image is the clear view of Neptune's rings. Some of these rings, faint and dusty, had not been detected since the Voyager flyby in 1989. The Webb telescope, with its enhanced capabilities, has refocused on these elusive rings. Neptune's rings are made up of bright, narrow bands of dust, as well as fainter ones. The Webb telescope's infrared images have put these rings in a new light, revealing features that were previously hidden in the darkness of space. This is the first time these rings have been seen in the infrared spectrum, providing new information on their composition and behavior. Like the planet itself, Neptune's rings are characterized by a unique composition, different from those of gas giants Jupiter and Saturn. Neptune is an ice giant rich in elements heavier than hydrogen and helium. This composition is also reflected in the characteristic blue color, invisible due to a small amount of methane gas in the visible spectrum. In the infrared images taken by the Webb camera near infrared camera, Neptune does not appear blue, in contrast to the dark appearance that would be expected due to the absorption of light and infrared by methane. In the images taken by the Space Telescope, Neptune appears as a luminous and bright sphere. This absorption also affects the appearance of Neptune's rings, as they reflect and refract the light that travels through the planet's atmosphere. This unexpected brightness in the infrared results from a unique interaction between the planet's atmosphere and infrared light. While methane gas absorbs red and infrared light, the high-altitude clouds in Neptune's atmosphere reflect sunlight before it is absorbed by the planet is absorbed. In the infrared spectrum, methane ice clouds appear as bright streaks and spots that cast a ghostly glow on the planet. By the way, you may wonder why Triton looks like a dazzling point of light adorned with bright spikes, in contrast to the fainter image of Neptune. These diffraction spike patterns are a feature of the imaging telescope. They are not physical structures, but optical artifacts created by the design of the telescope. The light from Triton passing through the mirrors and structure of the telescope is diffracted, giving rise to these striking peaks emitted by the moon. In simple terms, diffraction is what happens when a wave, such as light, travels through a small opening or around the edge of an object. Imagine light as water waves flowing through a narrow slit in a wall. When the waves pass through the slit, they deviate in different directions instead of going straight. This propagation of waves after passing through a hole or around an edge is what we call diffraction. In the context of the James Webb Space Telescope and its images, diffraction spikes arise due to the arrangement of the mirrors and structure of the telescope. When light from a bright object, such as a star or Triton in Neptune's images, enters the telescope, it is slightly deflected by the edges of the mirrors and other parts of the telescope. As a result of this deflection, the light is scattered and forms the star-shaped peaks that we see. The study of Neptune's rings, especially in the infrared, provides valuable information about the atmospheric conditions and internal composition of the planet. The interaction of the rings with Neptune's atmosphere, particularly with the methane ice clouds, provides information about the bright equatorial band that surrounds the planet gives clues about the global atmospheric circulation, a key factor in the planet storms. The atmosphere, which descends and heats near the equator, shines more intensely in the infrared than the colder gases that surround it. As we conclude our journey through the mysterious world of Neptune, we reflect on the impact these discoveries have on the broader field of planetary science and exoplanet exploration. Neptune, once a distant blue point, is now a testament to space exploration. The dynamic and constantly evolving nature of the discoveries about the true color of Neptune, its atmospheric phenomena, and the intricate details of its rings and moons go far beyond our solar system and provide a crucial example for understanding similar gas giants and exoplanets in our galaxy. The knowledge gained about Neptune will help astronomers decipher the mysteries of these distant worlds and enrich our understanding of the universe as we continue to contemplate the cosmos. Neptune reminds us of the unlimited potential of discovery. Its example encourages us to continue searching, asking questions, and unraveling the mysteries of the universe. Saturn has captivated the human imagination from ancient civilizations to modern astronomers. The Maori of New Zealand, separated by vast oceans and without telescopes, somehow knew that Saturn had rings. Thus the mystery deepens. Saturn has long been a symbol of the unknown and mysterious. Its iconic rings have been the subject of awe and speculation since the time of Galileo. But what if we told you that these rings, as eternal as they may seem, are actually a fleeting cosmic phenomenon that adds to the intrigue? A storm twice as wide as Earth with a mysterious hexagonal shape that has unleashed at Saturn's North Pole. What forces could have created such a geometrically perfect formation? But the mysteries don't end there. Saturn's satellites, Titan and Enceladus, offer conditions that could harbor life. Lakes of liquid methane and geysers that launch water and organic matter into space make these satellites more than just celestial bodies. They're possible homes for life. Join us to learn more about this enigmatic giant and its cosmic mysteries. Our journey begins with Galileo Galilei, the Italian astronomer who first pointed his telescope at Saturn in 1610. What he saw left him perplexed: a planet with something like ears. He did not realize that he was seeing the edges of Saturn's magnificent rings, a feature that would baffle astronomers for centuries. Galileo's telescope was primitive by today's standards, and the true nature of Saturn's ears remained a mystery. It was not until 1655 when Christian Huygens, armed with a more advanced telescope, correctly identified them as a system of rings surrounding the planet. As we entered the modern era, we witnessed the Pioneer 11 mission, the first spacecraft to fly by Saturn in 1979. This mission provided us with the first close-up images of the planet and its rings, revealing intricate details that were previously inaccessible to terrestrial telescopes. But it was the Cassini mission that truly revealed Saturn in all its splendor. Launched in 1997 and arriving at Saturn in 2004, Cassini spent 13 years studying the planet, its rings and its satellites, from the discovery of columns of water ice on Enceladus to the capture of the ethereal beauty of a hexagonal storm at the North Pole of Saturn. Cassini revolutionized our understanding of this distant world. And here is an interesting fact. Long before the arrival of telescopes, the Maori of New Zealand had myths that described Saturn with a pararo, or belt, around it. How they knew remains a matter of debate and speculation. But, as we will see later, Saturn hides more than one mystery. What do you think could have created a hexagonal storm with an area larger than Earth itself? Saturn is home to a geometric enigma at its north pole, a six-sided storm that has baffled scientists for decades. This six-sided wonder is not just a superficial feature, but a deep and lasting mystery that breaks the paradigms of fluid dynamics and planetary atmospheres. The hexagon was first discovered in 1981 by the Voyager spacecraft, but it was not until the Cassini mission, which orbited Saturn between 2004 and 2017, that we were able to see this cosmic spectacle firsthand. Cassini's high-resolution images showed a symmetrical jet stream surrounding the hurricane-like vortex in the center of the hexagon. Unlike Earth's chaotic weather systems, Saturn's hexagon is a masterpiece of geometric precision. So, what causes this hexagonal storm? Researchers at Harvard University have developed a 3D model that suggests that deep thermal convection in the outer layers of Saturn could be responsible. This model shows that the storm could extend thousands of kilometers into the depths of Saturn's atmosphere, far beyond what we can see. Interestingly, scientists have been able to reproduce the hexagonal pattern in a laboratory environment. Although these experiments do not capture all the nuances of Saturn's complex atmosphere, they provide a glimpse of extraterrestrial phenomena. Saturn's hexagonal vortex contrasts sharply with Earth's polar vortex, which is irregular and less stable. This difference raises questions about the fundamental properties that distinguish the atmospheres of gas giants from those of terrestrial planets. The longevity of the hexagon is another mystery, as it has been observed for at least 4 decades, and possibly much longer. This constant feature suggests that whatever feeds the hexagon is not a temporary phenomenon, but a stable, perhaps even permanent, aspect of Saturn's internal dynamics. Let us now turn our attention from the mystery of the hexagon to another wonder of Saturn. Saturn's rings are more than just a celestial jewel. They're dynamic, ever-changing systems that interest both astronomers and the general public. But what are these rings made of, and why are they so ephemeral? Saturn's rings are composed primarily of water ice, with a mixture of dust and rocky material. Their size varies from tiny particles to huge chunks the size of houses. These ice particles are not static, but are in constant motion under the influence of Saturn's gravity and the gravitational attraction of its satellites. The rings are divided into several subdivisions and gaps, each with its own unique characteristics. The most notable are the A, B, and C rings, separated by gaps, such as the Cassini division, a 3,000-mile gap between the A and B rings. The origin of Saturn's rings has been the subject of debate. A popular theory suggests they formed from the remains of a shattered moon. Another theory states that they are the remains of material from the formation of the solar system captured by the gravitational force of Saturno. Recent investigations have also shown that the rings may be much younger than Saturno itself, perhaps around 400 million years old, based on the rate of dust contamination. The rings of Saturno do not last forever. They are slowly disappearing due to a phenomenon known as ring rain, in which the particles of the rings are attracted towards the atmosphere of Saturno. This process is accelerated by the bombardment of micrometeorites and the interaction with the magnetic field of Saturno. At the current rate, some scientists predict Saturn's rings could vanish in 100 million years. The depletion of the rings would not only change the appearance of Saturn, but could also have consequences for its atmosphere and magnetic field. By stopping for a moment, we realize that even the most fascinating characteristics of our universe are not immune to the inexorable forces of physics, doomed to disappear in the chronicle of eternity. Saturno, the ringed giant of our solar system, is not only a celestial wonder, it is also a cosmic playground that contains some of the most intriguing satellites, 2 of which, Titan and Enceladus, have fascinated scientists and have raised a debate about the possibility of life beyond Earth. Titan is a world shrouded in mystery. Its dense atmosphere is rich in organic compounds, and there are lakes and rivers of liquid methane on the surface. But what is truly surprising is the speed at which Titan moves away from Saturn, 100 times faster than previously thought, which is the astonishing figure of 43 centimeters per year. This rapid drift suggests a dynamic, evolving relationship between Titan and Saturn. Could this drift affect the internal dynamics of Titan and perhaps even its potential for the existence of life? An atmosphere rich in organic compounds, such as nitrogen and methane, and the possibility of an underground ocean make Titan a tempting target for the search for extraterrestrial life. But the question remains, what would life be like in an environment so radically different from that of Earth? And let us remember Enceladus, another satellite of Saturn very different from Titan. It is an icy world with a highly reflective surface that outshines any other body in the solar system. Enceladus takes the concept of an ocean world to a new level. It not only has an underground ocean, but also expels it into space, where a space probe can collect samples. This ocean contains most of the chemical ingredients necessary for life, including hot, mineral-rich water that springs from hydrothermal sources. Hydrothermal sources can provide conditions necessary for life as we know it on Earth. These sources are teeming with life forms that thrive in extreme conditions. Could Enceladus' sources harbor similar, but alien, life forms? Enceladus also contributes to Saturn's Z-ring, a unique feature that further enriches the dynamic relationship between the Moon and its host planet. The icy particles of this ring open a window to the internal chemistry of the Moon, providing clues that could reveal its secrets. Titan and Enceladus are two moons orbiting the same planet, but with very different characteristics. Both present compelling arguments in favor of the possibility of life, fueling our curiosity as we contemplate the possibilities of life on the satellites of Saturn. It should be noted that our curiosity is not limited to telescopes and computer models. Upcoming missions aim to study these satellites up close and perhaps answer some of our most pressing questions. Meet Dragonfly, NASA's ambitious mission to Titan, scheduled for launch in the 2030s. This helicopter will fly over Titan's varied terrain, from dunes to impact craters. Dragonfly's main objective is to search for the basic components of life. It will analyze complex organic compounds in the atmosphere and on the surface, providing invaluable data on Titan's chemistry. Equipped with scientific instruments, Dragonfly seeks to understand the Moon's geological processes and how they relate to its potential to harbor life. Could Titan's unique chemical composition and liquid methane cycles offer a different recipe for life? Although there are no currently planned missions to Enceladus, the Moon's potential for life has made it an ideal candidate for future exploration. Scientists are proposing missions that could fly through Enceladus' plumes and take samples directly from its underground ocean. Such a mission could analyze the plume's chemistry for signs of life or prebiotic chemistry. The presence of hydrothermal sources in Enceladus' oceans adds another layer of intrigue, suggesting an environment in which life could thrive despite technical challenges. A mission to Enceladus could revolutionize our understanding of the potential for life in the solar system. It could provide direct evidence of the existence of extraterrestrial life, or, at least, clues about the conditions necessary for life to exist. Music. As we have mentioned, Saturn's rings are not eternal, as was once thought. Recent studies show that a process lasting hundreds of millions of years is causing these icy wonders to slowly fade. But how important is this for Saturn and its complex atmospheric dynamics? According to a study by the Japan Aerospace Exploration Agency, this material, composed mainly of water, causes a decrease in electron density in the atmosphere of Saturn. This phenomenon, known as ring rain, significantly affects Saturn's atmospheric conditions. Ring rain is not just a trickle, but a torrent carrying water in amounts equivalent to an Olympic swimming pool every half hour. The mystery is compounded by the relative youth of Saturn's rings, since, although Saturn is about 46 billion years old, data from NASA's Cassini missions suggest the rings may be only a few 100 million years old. This leads us to wonder, if Saturn's rings are so young, what catastrophic event could have led to their formation? Was it the destruction of a moon, or perhaps the capture of a passing comet? Cassini's space dust analyzer has added another layer of complexity. For 13 years, it collected 163 dust particles from outside the Saturn system. Surprisingly, the rings turned out to be quite clean, suggesting that they have not existed long enough to accumulate an excess of cosmic dust. This cleanliness raises the question, if the rings are young, why haven't they collected more cosmic dust? The absence of cosmic dust in the rings challenges our understanding of their age and interaction with the wider cosmos. It's as if the rings were in a cosmic laboratory or a clean room isolated from the dust permeating the rest of the solar system. As the rings are depleted, Saturn's appearance will undergo a dramatic transformation. These rings have been the task of the planet. Their disappearance would not only change the appearance of Saturn, but could also have unknown consequences for its atmosphere, perhaps even affecting the planet's albedo and heat retention. The loss of the rings could have a cascading effect on the atmosphere of Saturn, potentially altering wind patterns and even affecting the planet's iconic storms. The full extent of these changes remains unknown, making them a topic of intense scientific interest. Interestingly, the fate of Saturn's rings may be linked inextricably to that of its satellites. Some theories suggest gravitational instability may have destroyed some icy satellites orbiting Saturn, providing enough material to form the rings. The rings and satellites of Saturn are like companions in a cosmic dance, each affecting the other in subtle, yet significant ways. As we continue to study these celestial bodies, we can affirm the rings and satellites of Saturn are like companions in a cosmic dance, each affecting the other in subtle but significant ways. As we continue to study these celestial bodies, we can state that the fate of one can shed light on the mysteries of the other. In the vast theater of our solar system, where planets like Jupiter and Saturn often attract attention with their majestic rings and violent storms, lies a distant world shrouded in mystery and intrigue. This is Uranus, an enigmatic ice giant that often goes unnoticed, but holds secrets that could unlock some of the cosmos' most enduring mysteries. Beyond the asteroid belt, nestled between the orbits of Saturn and Neptune, Uranus travels through the cold, enigmatic ice giant that often goes unnoticed, but hides secrets that could unlock some of the cosmos' most enduring mysteries. Beyond the asteroid belt, nestled between the orbits of Saturn and Neptune, Uranus travels through the cold and dark corners of our solar system. It is a world that lives to a different rhythm, spinning on its side, a rarity that has puzzled astronomers and given rise to countless theories. Discovered in 1781 by William Herschel, Uranus was the first planet discovered through a telescope, expanding the known boundaries of our solar system. This distant world was nothing more than a point of light in our telescopes, a ghostly blue ball, distant and remote, guarding its secrets. But now, with the arrival of the James Webb Space Telescope, a new chapter opens in the exploration of Uranus. The JWST, with its unprecedented vision, uncovers the layers of this ice giant and reveals a world of incredible beauty and complexity. Let's travel together to this mysterious ice giant and learn about the latest discoveries made by the James Webb Space Telescope. In its quest to understand the universe, humanity has launched a sentinel into space, a marvel of engineering and a testament to our insatiable curiosity. This sentinel is the James Webb Space Telescope, the most advanced and powerful space telescope ever built, successor to the legendary Hubble Space Telescope, equipped with a set of advanced instruments and a mirror of more than 62. The JWST is designed to observe the universe in a light invisible to the human eye, the infrared spectrum. This allows the telescope to pass through clouds of cosmic dust, discover distant galaxies, and study the atmospheres of exoplanets. The telescope's journey into space was a feat in itself. Launched on an Ariane 5 rocket, the JWST traveled to a point in space known as the second Lagrange point, or journey into space was a feat in itself. Launched on an Ariane 5 rocket, the JWST traveled to a point in space known as the second Lagrange point, or L2, 1 million kilometers from Earth. Here, in this stable orbit, the JWST can observe the universe with minimal interference from the Earth and Sunday. The JWST's ability is not limited to observing the early universe or distant galaxies. but it plays a key role in unraveling the mysteries of our solar system. Its powerful instruments, such as the NIRCam near-infrared camera and the MIRI mid-infrared instrument, reveal new details about planets, moons, and other celestial bodies closer to us. Take Uranus as an example. In the past, our vision of this distant planet was limited to blurred images obtained with telescopes like Hubble. But now, thanks to the enhanced infrared capabilities of the JWST, we can see Uranus in a new light. The telescope's sensitive instruments allow us to observe its rings, weather patterns, and even its mysterious rings with unprecedented clarity. By analyzing the light from Uranus, the JWST can decipher the chemical composition of its atmosphere, revealing the presence of gases such as methane and hydrogen. This not only helps us understand the current state of Uranus, but also provides clues about its formation and evolution. The James Webb Space Telescope continues to exceed expectations and reveal more details about our universe every day. Its latest triumph is a series of very recent images of Uranus, surpassing even the impressive observations made in April 2023. In early 2023, the GWST provided us with unprecedented views of Uranus, allowing us to observe the planet's atmospheric dynamics and ring system in a new light. However, the recent images go a step further. Not only are they sharp, but they reveal aspects of Uranus that were previously hidden or blurred, even in the April observations. Take the rings of Uranus as an example. The latest images show them more clearly, allowing us to observe finer structures within the rings and even detect faint dust bands that were previously invisible, such as the Zeta Ring, the incredibly thin ring closest to the planet. The strength of the JWST lies not only in its one-off observations, but also in its ability to continuously track celestial objects. Continuous observations of Uranus have allowed us to observe changes in the planet's atmosphere, track the movement of its clouds, and observe the evolution of its storms over time. The changes in the polar regions are especially striking. The bright white layers and dark bands near the poles, whose origin is still unclear, have shown remarkable changes. This continuous observation provides valuable data for understanding the seasonal changes and long-term weather patterns of Uranus. Among the planets in our solar system, Uranus stands out for a peculiar characteristic, an extraordinary axial tilt, different from that of any other planet. Uranus rotates practically on its side, tilted at an angle of approximately 98 degrees. This unique orientation has long intrigued astronomers and has triggered a quest to understand its origin and its consequences. To understand the significance of this inclination, we must travel back to the early days of our solar system. Probably, Uranus formed with a much less pronounced inclination. The predominant theory suggests that a catastrophic event, perhaps a collision with an object the size of a planet, drastically changed its orientation. This colossal impact would have knocked Uranus over, changing the definition of its axis of rotation. Such a dramatic event in the planet's history probably not only changed its rotation, but also left a mark on its entire system, including its satellites and rings. Today, this lateral rotation is a unique spectacle. Each pole of Uranus is alternately flooded with sunlight and plunges into darkness at 42-year intervals. This extreme inclination gives rise to extreme seasons, unlike those observed on other planets. The implications for observation and planetary research are significant. The inclination of Uranus allows us to observe its rings and satellites from different perspectives, offering information about their dynamics and composition. For example, when the rings of Uranus are oriented towards Earth, they become almost invisible, revealing fainter bands of dust and smaller satellites. Compare this to Earth, which is inclined only 23 degrees. 5 degrees. The extreme inclination of Uranus causes drastic changes in its climatic patterns, a gold mine for scientists who study planetary climate. The inclination also affects the atmospheric circulation of Uranus. Prolonged exposure to sunlight from the poles can lead to complex climatic systems, as seen in recent images from JWST. These systems are very different from those of other planets and provide a unique laboratory to understand atmospheric physics. Let's travel through Uranian year. Each season on Uranus lasts about 21 Earth years, a result of its 84-year orbit around the Sun. This prolonged duration means that each hemisphere experiences long periods of daylight followed by equally long nights. As a result, the planet undergoes dramatic changes in its appearance and climate, as one pole of Uranus bathes in sunlight during the summers, while the opposite pole plunges into a deep winter. This stark contrast creates unique atmospheric conditions that lead to complex meteorological patterns and climatic changes. The impact of these seasonal changes on the atmosphere of Uranus is profound. When the sun illuminates the surface of the planet, it heats the atmosphere and creates colossal storms and dynamic cloud systems. These atmospheric phenomena are not static, but evolve and change with the seasons, painting an ever-changing portrait of the planet. Among the most striking characteristics are the bright cloud tops that appear when the sun illuminates the planet's atmosphere. These clouds, composed of frozen methane and other gases, reflect sunlight, creating spectacle. In contrast, dark patches of storms that look like giant hurricanes travel across the planet's surface. In addition, the planet's seasonal phenomena not only affect the planet itself, but also its moons. A recent study of the moons of Uranus, or rather, a particularly intriguing phenomenon, is the development of temporary atmospheres, a spectacle caused by the unique conditions of the Uranus system. The key to understanding these temporary atmospheres lies in the extreme inclination of the axis of Uranus and its effect on the orbits of the satellites. As these satellites orbit the planet, they experience drastic changes in solar exposure, alternating between long periods of intense sunlight and prolonged darkness. During the long summer, exposed to sunlight, the icy surfaces of these satellites undergo a process known as sublimation. The ice, composed mainly of water, methane, and carbon dioxide, transforms directly from solid to gas, without passing through the liquid phase. This sublimation creates thin temporary atmospheres, or exospheres, that envelop the satellites. These exospheres are more pronounced when the moons are warmer. Recent research from the James Webb Space Telescope shows that this phenomenon is more complex and dynamic than previously thought. The exospheres are heterogeneous, varying in composition and density depending on the moon's topography and the intensity of solar radiation. As the satellites enter their winter phase, the exospheres gradually dissipate. The gases recondense on the surface and return to an icy state. This cycle of creation and disappearance of the atmosphere is unique to the satellites of Uranus, opening a window to the interaction between solar radiation and surface ice. The rings of Uranus, often eclipsed by the majestic rings of Saturn, possess their own mystery and cosmic dynamism. A recent comparative study of the rings of Uranus, Saturn, and Jupiter sheds new light on these lesser-known, but fascinating, celestial features. Unlike the wide, bright rings of Saturn, the rings of Uranus are narrow, faint, and less extensive, extending up to 4 planetary radii, including elusive rings like the Mu and the New rings. The study delves into the gravitational influence of Uranus's main satellites on these rings, a key factor in their formation and evolution. The significant influence of the 5 main satellites of Uranus, Miranda, Ariel, Umbriel, Titania, and Oberon, plays a central role in the history of the rings. These satellites, much more massive than their smaller counterparts, dominate the gravitational dynamics within the Uranus system. Their positions and relative masses with respect to Uranus provide a better understanding of the satellite's formation and the gravitational formation of the rings. The formation of the rings of Uranus is attributed to a combination of processes including collisions, the rupture of satellites, and the release of gas from the main satellites. These dynamic processes affect the material composition of the rings and are influenced by the constantly changing environment of the Uranus system. The stability of the rings is intrinsically linked to their dynamic interactions with Uranus's satellites. The study examines how accretion processes occur within the Roche limit and how the dynamics of the shepherd moons play a crucial role in maintaining the rings. In addition, the rings offer a unique opportunity to understand the internal structure of Uranus through seismological studies. The model's results show how these satellites shape the ring system, affecting its structure and stability over time. The model predicts a significant loss of material within the ring system, mainly due to gravitational interaction with the satellites. The complex dance between the moons and the rings is a key aspect of the Uranus system. The dynamic exclusion zones created by the satellites and the influence of these zones on the distribution of the material of the rings are crucial to understand the structure and the evolution of the rings. The study also examines the role of the interactions between satellites in the evolution of the system, especially the past resonances between satellites like Ariel and Umbel and their impact on the orbits and the geology of the satellites, especially Miranda. But the mysteries surrounding this planet do not end there. You have probably heard of the aurora borealis, but the latest discovery refers to the auroras of Uranus, which also has them. However, unlike Earth's, these auroras occur in the infrared spectrum. Using the Keku telescope, the astronomers observed intensified emissions of trihydrogen cations in the atmosphere of the planet. This is a revolutionary discovery that sheds light on the unique magnetic field and the dynamics of the atmosphere of Uranus. The magnetic field of Uranus, which deviates significantly from the planet's axis of rotation, creates a unique configuration of magnetosphere, ionosphere, and thermosphere. The detection of these infrared auroras is crucial because it opens a new window into these processes, so far difficult to understand due to the lack of such detections on Uranus. Comparing the polar auroras of Uranus with those of Jupiter and Saturn reveals their different characteristics. Unlike Jupiter, where H3+ emissions have a short life that softens the variability of UV emission, the brightest infrared emissions of Uranus do not necessarily coincide with the brightest ultraviolet emissions of the other planets. This unique aspect of the polar lights of Uranus provides valuable information for the study of exoplanets, especially for the worlds of warm ice giants. The study delves into the unusual hot spots observed near the latitudes of Uranus's UV northern lights. These points, analyzed in terms of temperature, column density, and total emission, suggest that the increase is not caused by the temperature, but by a greater ionization, probably due to the activity of the polar auroras. The polar lights play an important role in heating the atmosphere, and, on Uranus, the increase in H3+ emissions associated with these auroras suggests their participation in atmospheric processes. By studying these unique phenomena, we obtain a deeper understanding of similar processes in different planetary environments, which enriches our knowledge about how auroras shape planetary atmospheres, affecting not only the thermal properties, but also the general dynamics of the ionosphere and the magnetosphere. In the search to unravel the mysteries of our solar system, the ice giants Uranus and Neptune are distant enigmas that invite closer exploration. Recent investigations, including a new analysis of Voyager images, have revealed that the two planets actually have similar tones of greenish-blue color, which radically changes our ingrained beliefs. Uranus and Neptune share many common characteristics. They are approximately the same size and mass, and are surrounded by deep atmospheres of comparable materials. However, for a long time, it was thought that their appearances were quite different. This error has now been corrected. Both planets are shown in their real colors, greatly influenced by the methane layer of their atmospheres. The need for a dedicated mission to Uranus has never been greater. Such a mission would not only deepen our knowledge of the planet itself, but would also provide a comparative view of Neptune and other similar ice giants. The potential objectives of the mission range from the study of the unique magnetic field and the complex ring system to the investigation of the atmospheric dynamics and the internal structure. In an important achievement for planetary exploration, the mission of the orbiter and the probe of Uranus has been elevated to the highest priority for the flagship mission of the NASA within the Decennial Survey of Planetary Science 2023 to 2032. Future launch windows are available between 2030 and 2034. Key scientific objectives will include a detailed analysis of the unusual inclination of the axis of Uranus and its effect on the climate and the weather patterns of the planet climate and the weather patterns of the planet. The mission will also be able to study the intriguing phenomenon of infrared auroras and their role in heating the atmosphere, providing a comparative study with other planets. The study of Uranus and Neptune will also provide valuable information about planetary evolution and dynamics. Understanding why Uranus appears slightly wider, perhaps due to its more stagnant atmosphere that allows the accumulation of methane haze, can tell us a lot about the atmospheric processes of ice giants. While we await a future mission to Uranus, we are on the threshold of discoveries that could redefine our understanding of the outer solar system. Exploring this distant ice giant will not only unveil its mysteries, but will also expand our knowledge of planetology as a whole, shedding light on the complex panorama of our cosmic home. The moon has always been a beacon of mystery and wonder, but beyond its radiant beauty and folkloric tales, the moon hides secrets that have eluded us for centuries. Among these mysterious characteristics is the lunar South Pole, a region shrouded in perpetual shadow and intense cold, untouched or explored by any previous lunar mission. This is the story of Chandrayaan-3, India's daring journey to unexplored territory. Launched on a journey of more than 238,000 miles, Chandrayaan-3 embarked on a mission not only of distance, but of discovery, with the purpose of unraveling the mysteries of the moon's South Pole, a place where sunlight barely reaches, an area where the terrain is so treacherous that you have to make your way through an endless maze of craters and rocks. Here, in this alien landscape, Chandrayaan-3 sought answers to questions that have puzzled scientists for decades. What is hidden beneath the surface of this mysterious region? Do earthquake-like tremors shake this silent world? And the most exciting question is whether water, the elixir of life, exists here as ice. When Chandrayaan-3 ventured beyond Earth, it carried the aspirations of a nation and the curiosity of the world. Its main objective was clear, but difficult to achieve: a soft landing near the moon's South Pole, a feat that had never been achieved before. From the busy Mission Control Center of the Indian Space Research Organization, a team of dedicated scientists and engineers piloted this ambitious mission. Their experience helped Chandrayaan-3 to cross the vacuum of space, overcoming the challenges of insertion into lunar orbit and descent. The South Pole of the Moon is a landscape unlike any other. Here, the terrain is a mosaic of craters and mountains, many shrouded in perpetual darkness. The challenge was not only to land, but to do so safely in an area where the terrain is relentless and most slopes are quite steep. When the Vikram landing module separated from the orbiter, it began its descent. The landing module, equipped with advanced sensors and engines, began its dangerous journey to the moon's surface. Imagine a spaceship navigating autonomously through a labyrinth of craters and rocks in search of terrain safe enough for landing. The systems on board the landing module worked tirelessly, analyzing every centimeter of the terrain that stretched out. In this treacherous landscape, the module also had to deal with extreme temperatures. The South Pole of the Moon is a place of extreme contrasts. The sun barely rises above the horizon, while the shadows hide frigid temperatures that can drop to minus 382 degrees Celsius. As the landing module made its final approach, the hearts in the Flight Control Center beat strongly. Every second was decisive, every maneuver a test of human ingenuity and technological prowess. With a slight bump, the Vikram landed, marking a historic moment not only for India, but for lunar exploration in general. In the silence of the lunar South Pole, Chandrayaan-3 began its mission of exploration and discovery. Thus, after the historic landing of Chandrayaan-3, a new chapter in lunar exploration began. The objective of the mission was to maximize the study of the characteristics of the moon, especially its elusive exosphere and ionosphere, and to establish the range of temperature variations just below its surface. The lunar exosphere, the thin layer of gases that surrounds a moon, holds the key to the satellite's past and present. Unlike Earth's robust atmosphere, it is so rarefied that it almost resembles a vacuum. The instruments of Chandrayaan-3, developed with the latest technology, are designed to measure the density and composition of this elusive layer. In addition to the exosphere, the mission delves into the lunar ionosphere. This layer, formed by solar energy that ionizes the atoms of the exosphere, plays a crucial role in lunar communications and navigation. The measurements of Chandrayaan-3 were designed to provide unprecedented information about the density and behavior of the ionosphere, important for future lunar missions and possible human habitats. Another intriguing aspect of the mission was the study of temperature variations just below the lunar surface using one of the landing module's 4 instruments, the CHASTE, or Chandra Surface Thermophysical Experiment. The temperature probe, submerged in lunar regolith, had the critical mission of mapping the thermal profile of the lunar soil. The results of Chandrayaan-3 revealed a strong contrast of temperatures on the surface during a lunar day. Temperatures rose drastically to 60 degrees Celsius. While at only 8 centimeters deep, they dropped significantly to minus 10 degrees Celsius, demonstrating the potential of the moon as a thermal insulator. This discovery opened new opportunities for future lunar habitats, as it suggests that the lunar regolith could serve as thermal insulation, protecting astronauts from the moon's extreme temperatures and harmful radiation. These studies were more than simple scientific efforts. They were a step forward towards a future in which the moon could be a gateway to space exploration. The results of the mission on the exosphere, the ionosphere, and the temperature of the lunar subsoil laid the foundations for understanding the environment of the moon and its potential to harbor human life. In the vast lunar landscape, Chandrayaan-3 was ready to detect a phenomenon that had not been observed in more than 50 years, a lunar quake. The mission managed to shed light on one of the most intriguing and least understood aspects of the moon. The Instrument for Lunar Seismic Activity, ILSA, a seismic instrument designed to detect the slightest tremors on the moon, achieved this. Chandrayaan-3 detected what appeared to be a lunar earthquake, a significant discovery, given that the last observation of this type was made during the Apollo missions in the early 1970s. Lunar earthquakes are fundamentally different from terrestrial ones. The seismic activity of the Earth is largely due to the movement of tectonic plates. The moon, which lacks these plates, experiences earthquakes for various reasons. These tremors can last much longer than earthquakes, sometimes up to an hour, and their origin is a subject of scientific interest. The data from Chandrayaan-3 suggests several possible causes for these earthquakes. One theory involves collisions with meteorites, which could cause shock waves that penetrate the lunar crust. Another is the gravitational force of the Earth, which causes tidal forces that load the lunar crust. Finally, extreme temperature fluctuations on the lunar surface can cause expansions and contractions that lead to earthquakes. These earthquakes are not only superficial phenomena, but windows into the interior of the moon. By analyzing the seismic waves, scientists can deduce the composition and structure of our satellite's interior, resembling an ultrasound of the lunar interior. This information is of great importance to understanding the formation and evolution of the moon. The detection of a lunar earthquake by the Chang'e-3 spacecraft has not only provided a glimpse into the dynamic nature of our celestial neighbor, but has also opened new perspectives on the geological processes that shape the moon to unravel its geological mysteries. Chandrayaan-3 carried out another exploration. Among the most intriguing findings is the discovery of sulfur, an element whose presence on the moon has been shrouded in mystery. The Laser-Induced Decomposition Spectroscope, or LIBS rover, a marvel of scientific instrumentation, vaporizes small samples of lunar soil using high-energy laser pulses. When the plasma emits light, the spectroscope analyzes its wavelength, thus revealing the presence of various elements, including sulfur. Sulfur's presence on the moon is a significant finding. On Earth, sulfur is often associated with volcanic activity, which raises questions about similar processes on the moon in the past. Its presence could provide information about the moon's volcanic history and the processes that shaped its surface. In addition to sulfur, another key objective of the Chandra 3 mission was the search for water ice, a search that has intrigued scientists for decades. Water ice on the moon is not only a scientific curiosity, but a potential resource for future human missions, providing water for life support and fuel production. Despite high hopes, Chandrayaan 3, like its predecessors, did not find direct evidence of water ice on the lunar surface of the moon. However, the lack of direct evidence is not a conclusion, but a clue that leads to new hypotheses. One theory involves the cold trap, in which water vapor can migrate to permanently shaded craters and freeze into ice. The detection of sulfur adds another layer to this theory, since sulfur can be trapped with water ice and released as a result of the decomposition of water molecules by high-energy solar radiation. The lack of direct evidence for the existence of water ice raises important questions. Is the ice at a greater depth under the surface, protected from detection by the insulating properties of lunar soil, or is its prevalence more heterogeneous and more difficult to detect than previously thought? During its exploration of the moon's south pole, Chandrayaan 3 found more than just sulfur. The LIBS instrument of the rover carried out the first in situ measurements of the elemental composition of the lunar surface in this region. In addition to sulfur, the instrument detected aluminum, calcium, iron, chromium, and titanium, each reflecting part of the complex geological history of the lunar surface. Other measurements added new details to this discovery, also revealing the presence of manganese, silicon, and oxygen. Each of these elements, with its own unique spectral signature, provided clues about the formation of the moon and its evolutionary history. Studies on the presence of hydrogen, a key component in the search for water, also continue. The mission's discovery of these elements and the ongoing search for water ice underscore the dynamic and complex nature of lunar geology. Each discovery, each unanswered question, brings us closer to understanding our closest celestial neighbor and prepares us for the next steps in lunar exploration. The Chandrayaan 3 mission to the south pole of the moon opened a new chapter in lunar exploration and also paved the way for the next ambitious leap, the Lunar Polar Exploration Mission, known as LUPEX. This joint initiative between the Indian Space Research Organization and the Japan Aerospace Exploration Agency is scheduled for 2026 at the earliest. 26. LUPEX plans to send an unmanned lunar lander and rover to continue exploring the moon's south pole region. JAXA will likely provide the H-3 launch vehicle and the rover, currently under development, and ISRO will provide the lander. This mission represents a significant step in international cooperation on lunar exploration. Are multiple. It will demonstrate new surface exploration technologies, fundamental for sustained lunar exploration in the polar region, and precise landings will be achieved through the use of a feature comparison algorithm and navigation equipment derived from the JAXA Smart Lander to investigate the lunar mission. The LUPEX rover will carry several instruments from JAXA and ISRO, including a drill capable of collecting samples at a depth of 15 meters. 5M. The search and analysis of water are key mission objectives, and the possible discovery of water ice could be a turning point for future lunar missions. Parallel to LUPEX, the ISRO Chandrayaan 4 mission, designed to bring samples back from the moon, is in the planning phase and is scheduled for launch in 2028. Chandrayaan 4 will consist of 4 modules: a transition module, a descent module, an ascent module, and a reentry module. The ambitious goal of the planned mission is to bring back soil samples from the moon, which will provide invaluable information about the lunar environment. The mission will involve complex maneuvers, such as sample collection, docking in lunar orbit, and the return of samples to Earth. The innovative discoveries of Chandrayaan 3, from the detection of sulfur and other elements to the study of lunar seismic activity, have revealed new layers of the moon's mysterious nature. These results provide crucial information about the moon's geology, its internal structure, and the potential for future lunar habitats. Looking ahead, lunar exploration is promising. Missions like LUPEX and Chandrayaan, which build on the legacy of previous ones, will continue to explore the mysteries of the moon. India's role in these efforts is not only that of a participant, but also that of a pioneer. These events inspire us to look beyond to the infinite mysteries of the cosmos. There are countless stories to tell in the universe, but one mystery veiled by the shadows of distant suns stands out among many others. This discovery invites us to look beyond terrestrial limits and to reflect on unknown possibilities. This is the story of Kepler-22b, a planet that not only wanders in the void, but enjoys the optimal point, the habitable zone of its star. Here, in this delicate balance, all conditions are met for the magic of life to ignite, for water to flow freely, and for the atmosphere to keep the secrets of existence discovered by the gaze of the Kepler Space Telescope. Kepler-22b invites us to reflect on what worlds may exist beyond our own, to question our understanding of life and our role in the universe. It makes us dream of new horizons of distant shores, where humanity could one day set foot. Today, we embark on a journey of discovery to unravel the mysteries of Kepler-22b and the countless worlds that await us beyond our reach, in the infinite expanses of space. In its search for Earth analogs scattered throughout the galaxy, the Kepler Space Telescope has become a pioneer, a celestial cartographer charting the unknown. Initially, Kepler's mission was very clear: to observe the immensity of the Milky Way in search of the faint twinkling of stars dimmed by the passage of planets in their orbit. Equipped with the most sensitive photometers, the telescope patiently observed the light of more than 150,000 stars. Among them, a pattern emerged: the rhythmic fading of a particular star, very similar to our Sun. This was the first indication of Kepler-22b, a planet that moved carefully around its star and briefly eclipsed its light, as if playing cosmic hide-and-seek. This discovery was a real event. The analytical skill required to examine huge data sets and select planetary transits from the cacophony of cosmic noise was immense. It was like detecting a faint difference in brightness caused by a moth flying in front of the beam of a lighthouse thousands of kilometers away. The transit method, Kepler's main tool, is a seemingly simple but very powerful technique. This method is based on the subtle interactions of planets orbiting their stars, passing in front of them for an instant and casting a small shadow that causes a slight dimming of the starlight. It is this faint and fleeting shadow that astronomers are looking for, a sure sign of a distant world orbiting its star. The elegance of the transit method lies in its simplicity and in the large amount of information it provides. When a planet passes in front of its star, it blocks some of the starlight, causing a measurable decrease in brightness. This decrease, detected by instruments like the Kepler photometer, is carefully analyzed to reveal not only the presence of the planet, but also its size. The amount of dimmed light indicates the size of the planet compared to its star. In addition, the regularity of these brightness variations reveals the orbital period of the planet, that is, the time it takes to orbit its star. This rhythm of disappearance and reappearance allows scientists to calculate the distance at which a planet is from its star, which provides crucial information about the planet's environment and its probability of being habitable. This method also opens a window into the planet's atmosphere. When the light of a star passes through the atmosphere of a planet during the transit, certain wavelengths of light are absorbed by the atmospheric gases. By studying these changes in the spectrum of the star, astronomers can determine the chemical composition of finding traces of molecules that may indicate the presence of water, oxygen, or even signs of biological activity. The discovery of Kepler-22b was a key moment in the search for Earth analogs. It highlighted the incredible potential of our technology and the perseverance of scientists. This discovery has brought us even closer to the path of space exploration, opening new chapters in the history of the search for worlds that could one day become a second home for humanity. In the variety of cosmic interactions between planets and stars, there is a delicate region, a narrow strip where conditions are perfect and where the hope of life as we know it endures in the darkness. This region, known as the habitable zone, is a cradle for potential life, a refuge where water can exist in a liquid state without boiling under the intense light of a star or freezing in the cold expanse of space. Imagine a world very similar to our Earth, located within this life-sustaining zone. Here, the heat of the star is neither too intense nor too weak, bathing the planet with a soft light. And here is where Kepler-22b orbits serenely in the habitable zone of its star, an ideal candidate in the search for conditions similar to those of Earth and, possibly, for life beyond our solar system. Just as Earth thrives in its zone, Kepler-22b enjoys a similar privilege by orbiting at a distance where temperatures allow the existence of lakes, rivers, and oceans. The presence of liquid water, universal solvent for many chemical compounds, is crucial since it is in the water where the chemistry of life develops. Water is the stage on which the drama of life unfolds, from the simplest bacteria to the most complex flora and fauna. However, the presence of water in a liquid state is only one of the many conditions needed to sustain life. What do we learn from analyzing this distant world? Is the theoretical presence of human beings on it possible? As we delve into the mysteries of Kepler-22b, we embark on a journey of discovery, reconstructing the puzzle of this distant world through the lens of our own Earth. With each observation, scientists get closer to understanding the fundamental nature of this distant planet, its size, its composition, and its atmosphere. These factors will help shed light on the presence of the basic components that could make this distant world a cradle of life. So what are these factors exactly? At the forefront of the search for life is, of course, the presence of liquid water, the cornerstone of all known biological processes on Earth. As we already know, Kepler-22b, which occupies a privileged position in the habitable zone, receives from its star a flow of energy that suggests that the temperature could be favorable to maintain water in a liquid state. While the presence of liquid water is a promising start, the composition and behavior of Kepler-22b's atmosphere remains a crucial mystery. The atmosphere that envelopes the planet is the most important determinant of the environmental conditions that affect surface temperature and pressure. Since the planet is in the habitable zone of its star, the theoretical presence of an atmosphere similar in composition to that of Earth, rich in nitrogen and with the necessary amount of oxygen and trace gases, could mean a temperate climate and stable water cycles similar to those that have fueled life on our planet for billions of years. However, the range of possible atmospheric scenarios is enormous and shrouded in uncertainty due to our current technological limitations to directly observe exoplanet atmospheres at such great distances. If the atmosphere of Kepler-22b tends to a denser composition dominated by carbon dioxide, like Venus, this could lead to a greenhouse effect. In such a scenario, any potential water would exist as supercritical vapor at extreme temperatures and pressures. Conversely, an atmosphere that is too thin and free of greenhouse gases could turn Kepler-22b into an icy world where water would only exist in the form of ice and the surface would be exposed to harmful cosmic radiation. The equilibrium temperature of the planet, estimated at a pleasant 22 degrees Celsius in atmospheric conditions similar to those of Earth, indicates the possibility of an environment with ideal conditions for life as we know it. However, if we went to the other extreme and created a greenhouse effect similar to that of Venus, the surface temperature could reach 30 degrees Celsius degree F, which would likely prevent the existence of life as we know it. Things get even more complicated. The elemental recipe for life goes beyond water and the right atmosphere. Life as we know it is intricately woven from a variety of chemical elements, among which carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur play a key role. Stars similar to the Sun, including Kepler-22, are G-type stars and usually have similar proportions of hydrogen and helium, with a small amount of heavier elements playing a fundamental role. However, during the formation of the planetary system, the distribution and concentration of materials in the protoplanetary disk around the star influence the subsequent composition of the planets. The temperature gradients in The distribution and concentration of the materials in the protoplanetary disk surrounding the star influence the subsequent composition of the planets and formation. Temperature gradients in this disk cause the condensation of different materials at different distances from the star, which affects planetary composition. Once a planet is formed, its composition can be altered by differentiation, that is, the separation of different materials within the planet, leading to the formation of distinct layers, such as the core, mantle, and crust, and by geological processes such as volcanic activity and plate tectonics. Therefore, although direct measurements of the chemical composition of Kepler-22b are beyond our capabilities, the diversity of elements in the universe and the location of the planet in a habitable zone can only hint at the exciting possibility of the presence of the basic components that create the basis of the complex chemistry of life. While we wonder if the planet's atmosphere could contain a protective layer like ours, or if it is a dense and oppressive mantle that traps heat as a result of the greenhouse effect. And what is the is really? One thing we know for sure. The last fourth parameter necessary for life agrees almost perfectly. The complexity of life must be fueled by energy, and the presence of Kepler-22b in the habitable zone guarantees its constant supply from the host star. This energy, which drives photosynthesis on Earth, could drive the fundamental biological processes necessary for life on this distant planet. The characteristics of a star, slightly cooler and smaller than our Sun, but similar in many respects, provide a stable source of light and heat against the grandiose landscape of the cosmos. Kepler-22b stands out as a beacon of possibilities, a world where the basic ingredients for life as we know it may exist, but the true nature of this distant planet remains shrouded in mystery, reminding us of the vast unknowns that await us as we continue to seek the secrets of the universe and the potential for life beyond our solar system. The search for signs of extraterrestrial life is a cornerstone of our celestial explorations, driving us to venture into the unknown with hope and scientific rigor as we turn our gaze toward distant worlds like Kepler-22b. The next generation of telescopes and space missions is ready to pierce the cosmic veil and invite us to observe the atmospheres of these distant planets and discover their secrets. At the forefront of this cosmic search is the James Webb Space Telescope, the most powerful and sophisticated space telescope ever built. With unprecedented resolution and sensitivity, the JWST is designed to observe the universe in the infrared, allowing it to detect the faint light from the first stars and galaxies, and more importantly, the atmospheric footprints of exoplanets. The JWST's suite of instruments carefully analyzes the light that passes through the atmosphere of exoplanets as they transit their host stars. This process, known as transmission spectroscopy, allows scientists to decipher the composition of the atmospheres of these worlds in search of characteristic molecular footprints essential for life, such as water vapor, oxygen, and methane. The mission of the Transiting Exoplanet Survey Satellite, TESS, launched in 2018 and complementing the JWST, is to study the nearest brightest stars in search of transiting exoplanets. Building on the legacy of the Kepler mission, TESS is expanding the search and revealing many new worlds for study, including planets that share characteristics with Kepler-22b, which will be priority targets for detailed atmospheric analysis, opening up new opportunities to search for biosignatures worth the Extremely Large Telescope, or ELT, which when completed will be the largest optical telescope in the world, will be another powerful tool in the search for extraterrestrial life. The colossal mirror of the ELT, located in the Cerro Arizon, in the Atacama Desert, in Chile, will collect the light from distant exoplanets, allowing direct images to be obtained and spectroscopic studies of their atmospheres to be carried out. Its advanced instruments will be able to detect even the faintest chemical footprints, further expanding our understanding of those distant worlds. Looking ahead, proposed missions such as the Habitable Exoplanet Observatory, HABEX, and the Large Optical and Infrared Observatory, LIR, equipped with advanced technologies like coronagraphs and star screens, promise to further expand the limits of exoplanet research. These observatories intend to obtain direct images of exoplanets by analyzing their light to reveal the molecular composition of their atmospheres in unprecedented detail. The search for extraterrestrial life and the exploration of these planets continues to inspire and stimulate the human spirit, reminding us that the search for life beyond Earth is more than just a scientific endeavor. It is a profound exploration of our place within the cosmos. As we stand on the threshold of discovery, our thoughts stray to the distant world of Kepler-22b, a planet nurtured in its habitable zone. Here, in this hypothetical realm, we imagine the possibilities that such a world could harbor. Could it be that the mountainous landscapes of this distant planet are home to a diversity of alien flora that thrives under the soft light of Kepler-22? Could it also be that its seas teem with life, with strange and extravagant forms adapted to the unique conditions of this distant world? And what would be humanity's potential role in such a world? For now, it is difficult to imagine, but these dreams are sustained by the relentless pursuit of knowledge that defines our current path in exoplanet exploration. As we look to the sky with instruments such as the James Webb Space Telescope, the Transiting Exoplanet Survey Satellite, and the upcoming Extremely Large Telescope, we continue to push the boundaries of our knowledge. Each discovery adds a piece to the great puzzle of the cosmos, revealing the diversity of worlds that inhabit our galactic neighborhood. The future of exoplanet exploration promises to deepen our understanding of distant worlds and redefine our place in the universe. As we stand at this crossroads of imagination and discovery, we remind ourselves that the search for life beyond Earth and the understanding of humanity's potential future among the stars reflects our deepest desire to explore, understand, and reconnect with the vast and wonderful cosmos that is our home. Is music the fabric of our universe, woven with the threads of time travel, or is it a tapestry of unattainable dreams? Our documentary series embarks on a quest through science and imagination, probing the limits of what we understand about the cosmos and our place in it. Can we bend time to our will, traversing the past and the future as easily as we travel from one place to another? We explore the tantalizing concept of time travel, delving into the realms of physics and fantasy to discover if our universe harbors the potential for such extraordinary journeys. What barriers stand between us and the realization of a warp drive, a technology that could break the cosmic speed limit established by Einstein's theory of relativity? We investigate the scientific obstacles and advances that raise the possibility of traveling faster than light and wonder what prevents us from building a warp drive in the cosmic ballet, where stars are born and black holes devour. The concept of white holes presents an intriguing counterpoint, a possibility that challenges our understanding of astrophysics. Could these theoretical inverse black holes that expel matter and light into the universe actually exist? What would their discovery mean for our understanding of cosmic evolution? Finally, we focus on a revolutionary discovery, a new law of nature that bridges physics and biology, offering a framework for predicting the course of evolution itself. How does this new law of nature redefine our understanding of life, its complexity, and its interaction with the physical universe? Join us as we explore these profound questions in search of answers at the intersection of known science and speculative theory. This series is an invitation to travel beyond the horizon of our current knowledge, to reflect on the mysteries that lie at the heart of existence. Welcome to a documentary experience where the impossible becomes a gateway to new realms of knowledge. Imagine a canvas of moments woven with the threads of time and matter that extends infinitely in all directions, capturing every choice, every event, every heartbeat. What if you could navigate this intricate fabric? What if you could go back in time, look to the future, or even change the course of history? Time governs our lives, but it remains one of the most mysterious phenomena in the universe. We measure it, we chase it, but can we control it? The concept of time travel has intrigued humanity for generations, inspiring countless works of fiction and sparking rigorous debates. But what does science say? Can time travel ever move from the pages of science fiction to the annals of scientific fact? The theory of relativity opened the door to this possibility by suggesting that time is not a constant, but a variable that can be manipulated. In addition, there are black holes, cosmic phenomena so powerful that they can distort not only light but time itself. Did you know that astronauts aboard the International Space Station age more slowly than humans on Earth, even if only by a fraction of a second? This is not science fiction. It is a proven consequence of traveling at high speeds. So let's travel through the corridors of time and explore the scientific paradoxes and the unlimited possibilities that one day could make time travel a reality. Welcome to a journey through time. Long before the advent of science as we know it, humanity was fascinated by the skies and the passage of time. Ancient civilizations paid attention to the stars, sun, and moon, creating elaborate calendars and methods for measuring time. Transported to the modern era, this fascination finds a new outlet in cinema and literature. The concept of time travel has been a recurring theme, offering both escapism and a platform for intellectual curiosity. In 1895, H.G. Wells wrote the novel The Time Machine, which, by the way, not only popularized the term time machine, but also introduced the idea that one could navigate through time as through the dimensions of space. Then came Back to the Future, a pop culture phenomenon that took the concept of time travel and made it accessible to a new generation. Who could forget the DeLorean, the flux capacitor, and the charming eccentricity of Doc Brown? But it is not just a Western phenomenon. The charm of time travel knows no cultural or linguistic boundaries, from the door of Jacques Stein to the profession of the Soviet Ivan Vasilievich. The theme of time travel resonates around the world. So, what attracts storytellers to this concept? The charm of rewriting history? The emotion of the unknown? Or perhaps the philosophical questions these trips raise? It is a desire fueled by a mixture of nostalgia and expectation, a longing to relive memories or launch into the promises of tomorrow. And now that we find ourselves on the cusp of scientific discoveries that could turn dreams into reality, the question becomes more important than ever. Could we? Should we? And what would happen if we traveled through time? The blackboard is the canvas on which the abstract becomes possible. Here, equations like mc²2 are not just symbols, keys to understanding the universe, but can they unlock the secret of time travel? From the big screen to living room televisions, time travel has been depicted in countless ways. But let's set fiction aside and delve into the science that can make time travel more than just a plot device. Let's meet space-time, the four-dimensional fabric of our universe, according to Einstein's theory of relativity. Einstein's theory of relativity. This fabric can be bent and deformed by mass and energy, but can it be torn or twisted to create a path through time? Time dilation, a consequence of Einstein's theory, suggests that time can flow at different rates depending on the speed of movement or the gravitational field. For example, astronauts on the International Space Station age slightly more slowly than people on Earth. Experiments with particles, accelerators, and atomic clocks have provided empirical evidence of time dilation. Particles traveling at speeds close to the speed of light have been observed to decay more slowly than their stationary counterparts. In addition, there are wormholes, hypothetical tunnels in space-time that, in theory, could shorten time and space. Although this is speculative, mathematics suggests they are possible. Leading physicists and cosmologists have expressed their views on the matter, offering theories ranging from the plausible to the bizarre. Some even suggest that quantum mechanics, the science of the very small, could play a role in making time travel possible. And let's not forget black holes, the mysterious titans of space. Their enormous gravity is so strong that it distorts not only space but also time itself. Could these cosmic phenomena be a gateway to other times? The scientific community is far from reaching a consensus. Time travel raises questions that challenge the very foundations of physics, from the nature of reality to the concept of causality. They say that time always moves forward and never backward. But what if we could jump forward, skipping years, decades, or even centuries. The idea might not be as far-fetched as it seems. When it comes to slowing down time, speed becomes the key parameter. According to Einstein's theory of relativity, the faster you move in space, the slower you move in time. So, could extreme speed be our ticket to the future? Believe it or not, travel to the future has already occurred, albeit on a minuscule scale. Astronauts aboard the International Space Station experience time dilation and age slightly more slowly than their counterparts on Earth. Let's now focus on the twin paradox, a famous thought experiment that takes time dilation to a new level. Let's imagine two twins separated at birth. One travels through space at a speed close to the speed of light, while the other remains on Earth. When they meet again, the twin who has traveled through space will appear younger. Reaching speeds close to the speed of light would greatly enhance this effect, but such speeds are currently beyond our technological reach, not to mention that the energy requirements would be astronomical. Scientists and engineers are grappling with these problems and investigating propulsion technologies that could one day make travel at speeds close to the speed of light possible. But even then, could the human body withstand such a journey? Let's imagine a future in which time dilation capsules are as common as airplanes, allowing people to jump into the future to glimpse advanced civilizations or even avoid catastrophes. Will knowledge of the future be a gift or a curse? And what will it mean for the concept of freedom? Music from science fiction to scientific articles. Wormholes have captured our collective imagination. These hypothetical tunnels in the fabric of space-time could end up being the cosmic shortcuts with which. But what are wormholes, and could they be the key to time travel? Imagine folding a piece of paper so that 2 points touch, then piercing it with a pencil through space-time. The wormhole would be that pencil, creating a direct path between two distant points. This concept gained popularity in the scientific community thanks, in part, to Carl Sagan. While writing his novel Contact, he consulted physicist Kip Thorne to explore the scientific possibility of using a wormhole for interstellar travel. Today, physicists are delving into the mathematics of wormholes. While the general theory of relativity allows for their existence, the equations also assume that they collapse too quickly for anything to pass through. In theory, by introducing some exotic matter, for example, the gravitational forces that cause the wormhole to collapse could be counteracted, keeping it open long enough for something or someone to pass through it. The representation of wormholes in popular media often overlooks these complexities. They are usually depicted as stable, luminous vortices, but the reality, if they exist, may be much more volatile and unpredictable. Despite the lack of empirical data, the study of wormholes is a dynamic area of research. Scientists use computer models and indirect observations to understand their properties and potential uses. Let's imagine the possibilities if wormholes could be used for time travel. One end could be anchored in the present and the other in the future or the past. The implications for research and even for the prevention of global catastrophes are astonishing. Wormholes open the door to questions not only about where we could go, but also when. As we approach the possible discovery of these cosmic shortcuts, we must ask ourselves if we are prepared for the responsibility that comes with such power in the world of the very small, where particles are also waves and reality itself seems diffuse. In the quantum world, this region of uncertainty could hold the keys to unlocking time travel. Quantum mechanics challenges our everyday understanding of the world. Let's take the double-slit experiment, in which particles behave as both particles and waves. Waves. This duality suggests that, at the quantum level, the fabric of reality is much more malleable than we thought. Great minds like Richard Feynman and Niels Bohr have delved into the mysterious world of quantum mechanics, a theory that has been incredibly successful in explaining the behavior of matter and energy at extremely small scales. Some physicists suggest that quantum mechanics could offer a basis for time travel. Quantum tunneling, for example, allows particles to pass through barriers as if they were ghosts through walls. In the double-slit example, can a similar principle allow time tunneling? Quantum computing is a new field that uses the principles of quantum mechanics to perform calculations at speeds unimaginable to classical computers. Some speculate that quantum algorithms could solve equations related to time travel that are currently too complex for current computers. The concept of quantum entanglement adds interest. Imagine two particles linked together in a certain way. Once entangled, these particles become interconnected, forming a single quantum system. The truly amazing aspect of entanglement is that the state of one particle instantaneously affects its entangled partner, regardless of the distance that separates them, whether on the other side of the room or even on the other side of the galaxy. Change the spin of one, and the other changes instantaneously. Albert Einstein famously called it spooky action at a distance. At first, he didn't like this idea because it seemed to violate the speed of light limit established by his theory of relativity. However, since then, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. He liked this idea, as it seemed to violate the speed of light limit established by his theory of relativity. However, since then, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. Could a remote effect like this make a difference in instantaneous time travel? Although the intersection between quantum mechanics and time travel remains a matter of speculation, it is a hot topic in scientific research. Researchers are studying everything from quantum loops in time to the role of quantum gravity in the early universe. Let's imagine a future in which the principles of quantum superposition could explain multiple timelines or realities. What if we could exist in a superposition of the past and the present? Could quantum mechanics be the final piece of the puzzle in our attempt to conquer time? Let's move on from the world of the microscopic scale to the grandly large. Black holes, mysterious titans of space whose gravity is so strong that not even light can escape. But could these celestial phenomena hold the secret to time travel? Enter the concept of closed time-like curves, CTC. A closed time-like curve is a path in spacetime that repeats itself. In theory, an object or even a person traveling along a CTC could end up at an earlier point in time. The idea was first proposed by physicist Kurt Gödel in 1949. The solution of Gödel to the field equations of Einstein suggested that rotating universes could contain loop trajectories in time. However, these solutions required specific conditions, such as a universe filled with rotating matter. Although the Gödel model is considered physically implausible in most cases, it has opened the door for other scientists to explore this concept. The main challenge is finding a scenario where CTCs can exist without violating the laws of physics. One such scenario involves rotating black holes, known as Kerr black holes. The enormous gravitational and rotational forces can, in theory, twist spacetime into loops, creating CTCs, but there is a drawback. Most models predict that the center of a rotating black hole, known as a singularity, will be ring-shaped instead of point-shaped. This ring-shaped characteristic could potentially serve as a gateway to CTCs. However, the powerful gravitational forces could also create a barrier known as the Cauchy horizon, beyond which the laws of physics are violated. The study of CTCs and black holes is rife with paradoxes and uncertainties. For example, if CTCs exist, they could lead to paradoxes where cause and effect are reversed. This has led some physicists to propose the chronology protection conjecture, which suggests that the laws of physics prevent such paradoxes. Imagine the possibilities and dangers of approaching a rotating black hole. Could we ever safely navigate through such a treacherous region of space-time? And if we could, what would we find on the other side? Another universe or another time? In addition to black holes and closed curves in time, there is another cosmic mystery that could open a path through time: cosmic strings. These hypothetical one-dimensional cracks in the universe could be remnants of the Big Bang. Cosmic strings are believed to have formed in the early universe, as it cooled after the hot, dense state of the Big Bang. These strings would have been thinner than an atom, but incredibly dense, and would have had tremendous gravitational force. Although still theoretical, cosmic strings offer intriguing possibilities regarding time travel. J. Richard Gott and William Hiskok have made significant contributions to our understanding of these mysterious objects. Gott suggested that a cosmic string traveling at the speed of light could, in theory, distort space-time enough to create a loop allowing travel to the past or future. However, the existence of cosmic strings remains a matter of debate. Their detection would require astronomical observations on scales that currently exceed our capabilities. Furthermore, if they existed, harnessing their power for time travel would be quite a challenge. Let's go back now to quantum entanglement. We have already explored how entangled particles are connected in ways that transcend ordinary spatial distances. Can they be united across time? Some theories suggest that entangled particles could be used to transmit information not only in space, but also through time. Let's imagine a future where quantum entanglement is used to create a quantum internet that allows instantaneous communication between eras. The intersection of cosmic strings and quantum entanglement is a frontier of theoretical physics, full of unanswered questions and untapped potential. Researchers are exploring how both phenomena could be connected and what this might mean for our understanding of time travel. Imagine a scenario where cosmic strings are manipulated at the quantum level through entanglement. This would represent a fusion of the very large and the very small, a meeting point between the cosmic and quantum scales that could revolutionize our concept of time travel. As we delve into the realm of time travel, we are faced with many paradoxes and enigmas. These are not just intellectual exercises, but fundamental questions that could make or break the possibility of time travel. First, there's the grandfather paradox. Imagine you go back in time and prevent your grandparents from meeting. If they never meet, one of your parents will never be born, and therefore, neither will you. But if you were never born, how could you travel through time? The grandfather paradox raises questions about causality and the very nature of time. Some theorists suggest that these paradoxes can be resolved through the existence of parallel universes, where each choice generates a new timeline. Another confusing paradox is the bootstrap paradox, which gets its name from the popular expression, pulling oneself up by one's bootstraps. Imagine you go back in time to give Shakespeare a copy of your plays, which he then claims as his own. In that case, where did those works originally come from? The bootstrap paradox creates a closed loop of cause and effect with no apparent origin. It challenges our linear understanding of time and suggests that cause and effect may not be as simple as we think. Another paradox, the predestination paradox, occurs when the actions of a time traveler in the past lead to the very event that he was trying to avoid. This raises questions about free will and determinism, and whether we can really change the course of history. The study of time travel paradoxes is not just a game for philosophers, but a serious area of research in physics and metaphysics. The resolution of these paradoxes could shed light on time travel. While we find ourselves on the threshold of scientific discovery, the future of time travel remains a mystery wrapped in paradoxes, theories, and cosmic phenomena. What was once the domain of science fiction is gradually approaching real science, from cosmic strings to quantum entanglement, through rotating black holes and nearby temporal curves. We have explored the theories and possibilities that one day could make time travel a reality. Current investigations are paving the way for new experiments, new technologies, and perhaps even a new understanding of the structure of reality. But as we teeter on the edge of cosmic horizons, one question becomes more important than all others. Are we prepared for what we might find? Time waits for no one, but what if we could wait for time for years? Has been a concept that challenges the laws of physics as we know them, a dream that has given rise to countless stories and science fiction fantasies. This mystery is the search for a warp drive, a technology that could allow us to travel great distances in space faster than light. Imagine a journey in which the limitations of time and space give way to the power of human ingenuity, where the farthest corners of the universe suddenly become accessible. This is not just science fiction, but a puzzle that scientists have been trying to solve for decades. Since the physicist Miguel Alcubierre proposed a theoretical model in 1994, the Alcubierre model, a bold combination of imagination and Einstein's theories, offers a way to curve the fabric of space-time. But what lies behind this bold idea? Is it just a fantasy, or could it be the key to unlocking interstellar travel? Today we explore the tangled web of problems and advances surrounding the warp drive, from the mysterious nature of negative energy to the problem of the entangled horizon. So let's dive into the depths of one of the most intriguing scientific quests of our time, the quest for the warp drive. Science or fiction in the heart of Mexico City. Amid the hustle and bustle of urban life, a young mind became fascinated by the mysteries of the cosmos. We're talking about Miguel Alcubierre, born in 1964, a physicist whose name has become synonymous with one of the most innovative ideas in theoretical physics. His journey began in Mexico and took him to the prestige. We are talking about Miguel Alcubierre, born in 1964, a physicist whose name has become synonymous with one of the most innovative ideas in theoretical physics. His journey began in Mexico and took him to the prestigious University of Wales, where he delved into the fields of general relativity and cosmology. In 1994, while working at the Max Planck Institute for Gravitational Physics in Germany, Alcubierre made a revolutionary discovery that challenged our understanding of space travel. Inspired by the iconic science fiction series Star Trek, he posed a bold question. Could the laws of physics allow for a real warp drive? Let's analyze the Alcubierre engine. Let's imagine a spacecraft that does not move through space in the usual sense, but is inside a space-time bubble. This bubble, or warp bubble, is the key to the Alcubierre concept. According to Einstein's general theory of relativity, massive objects distort the fabric of space-time. Alcubierre hypothesized that if we could manipulate space-time in a controlled way, we could create a warp bubble. The space in front of the bubble is compressed, pushing the bubble forward, while behind it the space expands, pushing it from behind. Inside this bubble, the spacecraft remains stationary, but the bubble moves, allowing the ship to travel faster than light without violating the laws of physics. This idea does not involve moving the spacecraft at high speed, but is about moving the space around it. It is like putting a surfboard or a spacecraft on a wave, a warp bubble, and letting the space-time ocean carry it. However, the Alcubierre model is not simply a manipulation of space, but requires exotic matter with a negative energy density to stabilize the warp bubble. This exotic matter is one of the many theoretical obstacles that scientists face when trying to turn the Alcubierre thruster from a fascinating theory into reality. As we delve into the practical aspects of the Alcubierre thruster, we face enormous challenges that stand between theory and reality. The first of these is the scale of energy and mass requirements. It was originally thought that creating a warp bubble would require an amount of energy equivalent to the mass of the observable universe, an unimaginably enormous amount, far beyond our current technological capabilities. However, the field of theoretical physics is constantly evolving. A remarkable achievement was when physicist Chris van den Broek proposed modifications to the shape of the warp bubble. These adjustments drastically reduce the energy requirements to approximately the mass of 3 suns, a colossal amount, but a significant step from the original estimates. The second major obstacle is the need for exotic matter and negative energy in the Alcubierre model. This exotic matter is crucial to stabilize the warp bubble and make it work as intended. Negative energy is a peculiar and controversial concept. It is a concept of physics that can distort the very structure of space-time. It is not just the absence of energy, but a real physical quantity with negative characteristics. In the context of the Alcubierre engine, negative energy counteracts the effects of normal positive energy, creating the conditions necessary for the existence and stability of the warp bubble. Negative energy in the context of the Alcubierre engine is, without a doubt, a complex and somewhat difficult concept to understand in physics, and it is important to distinguish it from more familiar concepts such as gravitational potential energy in classical physics. The concept of negative energy often refers to gravitational potential energy. For example, the gravitational potential energy of an object in a gravitational field, such as a planet, is considered negative energy because it is needed to move the object from the source of gravity to a point where this energy would be zero, for example, to infinity. This form of negative energy is the cornerstone of our understanding of gravitational interactions in the universe. However, the negative energy needed for the Alcubierre drive is different in this context. Negative energy refers to a hypothetical form of energy. The energy density is less than zero. It is not just an accounting tool or a wave that describes the potential energy in a gravitational field, but a real physical substance or field with exotic properties, such as repulsive gravitational effects. This type of negative energy is not something we observe or fully understand in the context of known physics. However, the existence of negative energy and, by extension, of exotic matter remains a topic of intense debate and speculation in physics. Although phenomena, such as the Casimir effect, suggest the possibility of negative energy under certain conditions, harnessing it to the scale necessary for a warp engine is a challenge. These challenges, the enormous energy requirements and the need for exotic matter, underscore the monumental task of transforming the Alcubierre engine from a theoretical model to a practical reality. They not only represent technological obstacles, but also fundamental questions about the nature of the universe and our ability to manipulate its basic forces. As we move toward the world of warp engine technology, we face another obstacle known as the horizon problem. This problem lies at the heart of the Alcubierre engine's design and poses serious issues for its practical application in astrophysics. The horizon is often referred to as the limit beyond which events cannot affect an outside observer. The most famous example is the event horizon of a black hole, the point of no return. Beyond this horizon, the gravitational attraction is so strong that nothing, not even light, can escape it. Similarly, in the Alcubierre engine, the horizon is the limit of a warp bubble. Inside this bubble, the spacecraft is isolated from the rest of the universe, just as the interior of a black hole is isolated from the outside world by its event horizon. The horizon problem arises from the warp bubble's unique structure itself. In the Alcubierre model, the spacecraft is located in a region of the space-time plane surrounded by a warp bubble that compresses space in front and expands it in the rear. This manipulation of space-time allows travel at speeds greater than that of light, but with a critical limitation. It isolates the spacecraft from the rest of the universe. Imagine being inside this warp bubble. The very mechanism that allows you to travel great distances in space also prevents you from controlling the ship or interacting with the outside world. Communication signals, navigation orders, and even visual observations are impeded by the bubble's limits. Passengers and crew will not be able to control the ship, correct its course, or stop the journey once it has begun. The implications of the horizon problem are profound. It implies that a warp-powered spacecraft would essentially be traveling on a one-way, uncontrolled journey. This raises practical questions about the use of such technology for exploration or travel. How do we get to specific destinations? How do we avoid collisions with celestial objects or adjust our flight path to cope with unforeseen circumstances? In addition, this problem implies the need for a pre-established infrastructure similar to an interstellar highway with mechanisms to create and control the warp bubble from outside. This requirement adds another layer of complexity to the already difficult task of making warp propulsion technology a reality. While the horizon problem represents a major engineering challenge, it is important to recognize that it invalidates the fundamental scientific validity of the concept. In theory, the principles underlying the warp engine remain sound and plausible within the framework of the general theory of relativity. As we delve into the complexities of the Alcubierre engine, we encounter another major problem, the radiation problem. This problem is twofold. as it involves both the accumulation of radiation at the front of the warp bubble and the potential effects of Hawking radiation within the bubble itself. First, consider the radiation that accumulates at the front of the warp bubble. As the bubble moves through space at a speed greater than that of light, it inevitably encounters interstellar particles and cosmic radiation. These particles and radiation, unable to pass through the warp bubble, accumulate near its leading edge. Such accumulation poses a significant risk when the warp bubble slows down or stops, as the accumulated radiation and particles are released in a burst of energy. The intensity of this release could be catastrophic, not only endangering the spacecraft and its passengers, but also potentially damaging any nearby objects at the destination. As we move within the warp bubble, we encounter the second aspect of the radiation problem, Hawking radiation. This theoretical radiation, predicted by Stephen Hawking, arises from the effects of quantum mechanics near the edges of black holes. In the context of the warp engine, the intense deformation of space-time around the edge of the bubble could create conditions similar to the event horizon of a black hole, potentially generating Hawking radiation. This radiation could have harmful effects on passengers inside the bubble, exposing them to high levels of energy and particles. The implications of these radiation problems are profound. Not only do they pose serious engineering and safety challenges, but they also raise questions about the feasibility of long-duration travel using the Alcubierre engine. Ensuring the safety of passengers and the integrity of the spacecraft against these radiation hazards is a critical area that requires further research and innovative solutions. This is a challenge that requires ingenuity and a deeper understanding of the interaction between quantum mechanics, the theory of relativity, and the harsh reality of space travel. When we turn our gaze to the current state of research in warp propulsion technology, we find ourselves in the midst of active scientific research. In recent years, numerous articles and theoretical papers have appeared, opening new paths in this field. One of the most notable advances is the work of physicists who have revised the energy requirements of the Alcubierre engine based on previous advances that significantly reduce the estimated energy requirements. Recent articles have proposed several methods to further optimize the geometry of the warp bubble. These improvements aim to make the energy requirements even more feasible, approaching the realm of possibility. Researchers, such as Harold White, who played a key role in experimental work at NASA's Eagle Works laboratories on the feasibility of warp bubbles and space-time manipulation, have made significant contributions to this field. Another area of active research is the exploration of alternative theories that could circumvent some of the limitations of the Alcubierre engine. For example, some physicists are exploring the possibility of using solitons, solitary waves that retain their shape as they travel at a constant speed, as a basis for creating stable warp bubbles without the need for negative energy. There is also growing interest in the role of quantum mechanics in warp engine physics. Researchers are delving into the quantum aspects of space-time and how they might affect the mechanics of a warp engine. This includes studying the effects of quantum entanglement and the potential use of quantum fields to stabilize the warp bubble. The recent theoretical advances also include the study of the effects of the warp engine technology on causality and the structure of space-time. These studies are fundamental to addressing possible paradoxes and time travel scenarios, guaranteeing the concept continues to base itself on physical laws as we know them. Little by little, the dream of the warp propulsion technology is getting closer and closer from the pages of science fiction to the scope of scientific possibilities, driven by the tireless efforts of researchers around the world. As we reflect on the future of warp propulsion, we find ourselves at a crossroads of assumptions and possibilities. The realization of the warp propulsion, a concept that before was limited to the scope of science fiction, depends on several key advances and discoveries. In the first place, the theoretical problems associated with the warp propulsion technology must be addressed. Among them, finding viable solutions to the enormous energy requirements, the creation and stabilization of warp bubbles, and the safe management of radiation risks. The advances in areas such as quantum mechanics, exotic matter, and the manipulation of energy are fundamental to convert these theoretical possibilities into a practical reality. Beyond the scientific and technical obstacles, the arrival of warp propulsion entails many ethical and practical considerations. The capacity to travel great distances in space at unprecedented speeds would revolutionize space exploration and open new horizons for humanity. However, great power brings great responsibility. The ethical implications of said technology must be carefully considered, which includes the potential impact on space ecosystems, the responsibility of exploring and possibly interacting with extraterrestrial life, and the equitable access to this technology among the nations and the peoples. In practice, the warp propulsion technology could lead to new methods of utilization of the resources, new ways of carrying out scientific research, and even the possibility of interstellar colonization. This would fundamentally change our relationship with space, going from exploration to habitability and utilization. For now, we await with interest a future in which the stars are not only points of light in the night sky, but destinations within our reach. This future promises unexplored territories and unprecedented exploration, inviting us to continue our search for knowledge and discovery. Music. There is an interesting mystery in our world generated by the equations of the general theory of relativity of Einstein. It is the theoretical analog of the black hole that many know. We call it a white hole. Let's imagine a region of space in which, unlike a black hole that consumes everything, nothing can penetrate. Instead, this cosmic anomaly defies our expectations by expelling matter and energy that shine violently in the dark grays of space. In a universe governed by the concept of the arrow of time, where events flow from the past to the future, a white hole is a tempting paradox. It is like watching a space movie in reverse, where the rules of gravity and time seem rewritten. But are these celestial wonders only mathematical curiosities, or do they contain the key to understanding the deepest truths of our universe? Let's delve into the mysteries of white holes, exploring their theoretical foundations, their enigmatic characteristics, and their potential role in the grand story of the universe. At the beginning of the 20th century, Albert Einstein revolutionized our understanding of the universe by creating the theory of general relativity. This revolutionary theory proposed a radical idea. Gravity is not a force that attracts objects, but a curvature of space-time caused by mass and energy. Let's imagine space-time as a stretched fabric, like a cosmic trampoline. When an object with mass, like a star or planet, lands on this fabric, it causes a depression. This curvature directs the movement of other objects that move along curved trajectories in space-time. This is gravity as Einstein imagined it. Einstein's theory led to the prediction of black holes, regions of space with a gravitational force so strong that nothing, not even light, can escape them. These cosmic giants are formed when massive stars collapse under their own gravity, distorting space-time to the extreme. We present Carl Schwarzschild, a brilliant physicist who, while fighting in the First World War, found an interesting solution to Einstein's equation. The Schwarzschild solution described the space-time around a non-rotating spherical mass, like a star. Schwarzschild's work laid the foundations for understanding black holes, but also hinted at something even more mysterious. If a black hole is a region from which nothing can escape, could its opposite pole exist, a region into which nothing can enter, only exit? This gave rise to the concept of a white hole. Just as a black hole is the final point of gravitational collapse, a white hole could be considered an inverse black hole, a source of cosmic energy that expels matter and energy. However, unlike black holes, which have already been observed, white holes remain a theoretical concept, a tempting possibility in the vast cosmic mystery of astrophysics. The path from mathematical abstraction to physical reality is often long and difficult, and white holes are no exception. These theoretical entities arise from the complex equations of general relativity, the same mathematical structure that predicts the existence of black holes. The mathematics of white holes are solid, but it is like a puzzle with missing pieces. We understand its theoretical basis, but the real challenge is relating these mathematical models to observable phenomena. Let's imagine a universe in which, instead of collapsing inward, a region of space-time does the opposite. It explosively expels matter and energy. This is the essence of a white hole, a mirror image of a black hole in which the flow of time and matter is reversed. But can these mathematical abstractions exist in our physical reality? The debate among scientists is continuous and multifaceted. Some theorists suggest that white holes could be remnants of the early universe, exotic structures interwoven into the fabric of space-time. Others suggest they could represent the other end of a black hole, a kind of cosmic exit door from which matter and energy reappear after being swallowed by the black hole. The novel idea of quantum gravity suggests that as a black hole evaporates over eras and loses mass, it may reach a point where it can no longer sustain itself as a black hole, and that point may become a white hole that releases the trapped content back into the universe. However, there exist serious problems with the physical existence of white holes. The laws of thermodynamics, especially the concept of entropy, pose a serious obstacle. Entropy, a measure of disorder, tends to increase in the universe, while white holes, by nature, decrease entropy, contradicting this fundamental principle. Furthermore, the stability of white holes remains a controversial topic. Some theories suggest that, if they formed, they would be extremely unstable and would probably collapse almost instantly into black holes in space. White holes represent one of the most enigmatic and paradoxical concepts. These mirror images of black holes have characteristics that challenge our traditional understanding of physics. Let's understand in more detail what the concept of a white hole in theoretical physics is. At the center of a white hole is its event horizon, a limit not of escape, as in black holes, but of impenetrability. This event horizon marks the point at which matter and energy are expelled, creating a spectacle of cosmic proportions. Unlike a black hole, which absorbs everything, a white hole is a source of expulsion, the cosmic source from which matter and energy arise. One of the most intriguing aspects of white holes is the concept of time reversal. Time usually flows in one direction, from the past to the future. However, white holes seem to reverse this flow. It is like watching a science fiction movie played in reverse, where the usual rules of time and space are reversed. By delving into the nature of white holes, we face a realm of paradoxes and problems. One of the most important is its connection with the entropy mentioned above. According to the second principle of thermodynamics, entropy, or a measure of disorder, must always increase in a closed system. However, white holes seem to ignore this law, decreasing entropy and expelling matter in an ordered state. This apparent violation of thermodynamic laws presents a serious problem for our understanding of physical processes in the universe. How can an object like a white hole exist if it contradicts such a fundamental principle? Another paradox lies in the concept of the arrow of time, or how the universe advances inexorably in time. White holes suggest a scenario in which time can flow backwards, at least from a certain point of view. This concept breaks not only our understanding of time, but also the very nature of causality. Let's summarize the characteristics of white holes. Their event horizons, the expulsion of matter, and the concept of time reversal present a fascinating but paradoxical panorama. Despite the theories that seek to solve these problems, white holes remain in the realm of theoretical physics. As we delve into the mysteries of the cosmos, the concept of white holes invites us to rethink our understanding of the universe. These theoretical objects are not only surprising anomalies, but may have profound cosmological implications. Let's consider the Big Bang, the colossal explosion that marked the beginning of our universe. Some theorists suggest that this crucial moment in cosmic history was not just a random explosion, but that the event may have been a white hole of unimaginable magnitude, an eruption of matter and energy that gave rise to the cosmos. This vision offers a radically new interpretation of the origin of our universe, suggesting that white holes could play a role in cosmic genesis. Let's imagine a white hole not only as a theoretical construct, but as the very source of the creation of our universe. In this scenario, the Big Bang could be conceived as a white hole of immeasurable scale that expelled matter, energy, and space-time, which subsequently evolved into the stars, galaxies, and planets that we observe today. This vision offers a radical rethinking of the Big Bang. Instead of an indefinite singularity, we have a white hole, an entity defined by the laws of physics, although in a form that pushes our understanding to the limit. This white hole could have been the first spark that set the stage for subsequent cosmic evolution. If the Big Bang was really a white hole, profound questions arise about the nature of our universe. What was the origin of this white hole? Was it the result of the collapse of a universe from another dimension, or the result of processes that surpass our current scientific understanding? This concept also changes our perception of time and causality. If the Big Bang was a white hole, it suggests the existence of a universe with a more complex timeline in which the beginning and end of cosmic phenomena are intertwined in ways that we do not yet understand. This idea of the Big Bang as a white hole combines organically with the Big Bounce theory, according to which the beginning of our universe could be the result of the collapse of a previous universe. It unites the idea of cyclic universes, suggesting that each cosmic end can give rise to a new beginning similar to the explosive genesis of a white hole. The existence of white holes could also confirm the concept of parallel universes. If white holes can expel matter and energy, could they be a gateway to other universes? This possibility is related to the multiverse theory, which postulates the existence of multiple universes, possibly infinite, along with our own. In parallel universes, there could be different versions of physics, alternative histories, and perhaps even variations of ourselves. Another intriguing connection refers to wormholes, hypothetical tunnels in space-time. Theoretical models suggest that wormholes could connect distant regions of space and perhaps even different universes. If white holes are connected to wormholes, they could serve as cosmic portals that open paths to remote corners of the universe or even to other dimensions. This connection raises tempting questions about the nature of space and time. Could white holes and wormholes allow travel through vast cosmic distances or even between universes? Looking towards the future of astrophysics, we see that for the moment, there's a lot of scientific research that in one way or another affects the topic of white holes. But two research articles stand out from the rest, shedding light on the mysterious nature of these cosmic objects and offering new ideas and possibilities that could revolutionize our understanding of them. The first article takes us on a journey to the limit of black and white holes, exploring the close connections between them and refocusing on the physics that occurs near their horizons. The authors introduce the concept of coordinate systems that penetrate the horizon, a revolutionary approach that allows us to distinguish between the horizons of black and white holes. These differ from standard curvature coordinates in a small region near the horizon to emphasize the distinction between black and white horizons, which depends on the physics near it. The study suggests that black holes might not be the cosmic dead ends we once thought, but could be in quantum superposition with white holes, creating a scenario in which observed phenomena could hint at the existence of these theoretical counterparts. The article also delves into the role of quantum physics in these regions near the horizon, suggesting that quantum effects may dominate, with important implications for our understanding of white holes. However, the authors emphasize a problem in observational astrophysics, in which there is substantial observational evidence for the existence of black holes, but relatively weak support for white holes. Moving on to the second article, entitled New Black to White Hole Solutions with Improvised Geometry and Energy Conditions. New solutions from black holes to white holes with improvised geometry and energy conditions. We find that the focus here is on how to turn black holes into white holes. Guided by the principles of quantum gravity, the study presents models in which the effects of quantum gravity prevent the formation of singularities within black holes, providing a smooth transition to white holes. This resolves the paradox of information loss by assuming that matter can pass through a black hole and appear in a white hole. The article also explores the geodesics within these models, confirming the completeness of the paths of particles in the transition from the black hole region to the white hole region. This supports the idea of a continuous and unhindered flow of matter, which changes our understanding of these cosmic phenomena. By integrating these theoretical developments with emerging technologies, we are on the threshold of a new era in astrophysics. Research on white holes promises to reveal new aspects of the universe, where the boundaries between quantum mechanics and general relativity blur. In summary, we can say that the future of research on white holes is promising. Who knows, perhaps very soon we could discover evidence of the existence of these intriguing objects. Music. Our universe hides a mystery that has long captivated the human mind, a question that bridges the known and the unknown, the simple and the complex. Here on Earth, life thrives in a continuous movement of order and chaos. Each life form is evidence of a hidden order, a pattern woven into the very fabric of existence, from the smallest microorganisms to the largest mammals. But what if the complexity of life, the very essence of our existence, could be explained not only through the lens of biology, but also through a mathematical framework? This is the territory of assembly theory, a revolutionary concept that transcends traditional science. It is a journey into a world where mathematics and biology converge to reveal the hidden architecture of life. Imagine a universe in which the secrets of life, from the simplest molecule to the most complex organism, are encoded in mathematical language and waiting to be decoded, where the line between the living and the inert blurs, giving rise to new possibilities and knowledge. Let's explore how this revolutionary idea is changing our perception of life, evolution, and the cosmos itself. And perhaps we can even get closer to answering the fundamental question: what is the true nature of life in the universe? Since the dawn of civilization, mathematics has been the language of the universe, a tool for deciphering the mysteries of nature. But how does this language of numbers and equations relate to understanding the very essence of life at its core? Assembly theory offers a simple but profound idea. The complexity of life can be measured and understood through a mathematical prism. Think of life as a puzzle in which each piece represents a molecular block. Assembly theory seeks to show how these pieces come together step by step to form the complex structures that define living organisms. Each step in this assembly process represents a leap in complexity, from simple atoms to complex proteins. The theory introduces the concept of the assembly index, the cornerstone of this theory, which measures the number of steps required to build a biological structure. It is a numerical value that captures the essence of complexity by quantifying the immeasurable. But how does the standard model of physics fit into this? The standard model of physics describes the fundamental particles and forces that govern our universe. It seems completely separate from the complexities of biology. However, assembly theory bridges both fields. In the field of assembly theory, the standard model lays the foundation for understanding forces and interactions. It is a bridge between the microscopic world of quarks and leptons and the macroscopic world of living beings. Another important element of the theory is the concept of studying dynamic systems, the phase space. This is a mathematical concept used to describe all possible states of a system in the context of assembly theory. The phase space allows us to trace the path of the assembly of life from a single point, representing the simplest form of life. The phase space expands, branching into almost infinite possibilities, and each path represents a different route that life can take in this unlimited mathematical landscape. The trajectories of evolution and its complexities unfold in this mathematical framework, offering us a new perspective on the complexity of life. It is not only about the particles and forces described by the standard model, but about how these elements combine and interact over time to create the diverse pattern of life that we see. This is where the chaos of random molecular interactions gives way to the order of living structures. So let's ask ourselves this question: are the complexities of life simply a product of chance, or is there a deeper cause? Let's consider two contrasting concepts: complexity and entropy. Entropy, a measure of disorder and randomness, seems to contradict the complexity we observe in life. How do these opposing forces coexist in the natural world? This is where assembly theory offers a revolutionary perspective. A central element of assembly theory is the assembly index, a tool designed to measure the complexity of life. Think of it as a cosmic ruler that measures the steps needed to assemble a biological structure from its simplest components. Imagine that a single molecule is the starting point on this scale. As you go up the scale, each step represents a more complex assembly, from molecules to cells and beyond. The higher the index, the greater the complexity, and the less likely it is that the structure has arisen by chance. Now let's delve into the interaction between entropy and delve into the interaction between entropy and complexity. Entropy, a concept rooted in thermodynamics, suggests that systems tend naturally to disorder. However, life defies this trend, evolving from simple origins to a variety of complex forms in the ordered structures we see today. How does assembly theory resolve this apparent contradiction? It suggests that life is inherently a process of overcoming entropy. Through the prism of the assembly index, we see that the complexity of life is not a challenge to entropy, but a journey through it. Let's consider early Earth, a primordial soup of simple molecules. Over millennia, driven by the laws of physics and chemistry, these molecules began to assemble into more complex structures. Each step along the way marked a victory over entropy, a step toward greater complexity in life. By rethinking evolution through assembly theory, we see it not as a mere biological process, but as a mathematical inevitability. The emergence and evolution of life became a story of increasing complexity, written in the language of mathematics. Let's now move on to a trivial question, but one that offers us a new perspective. Are we alone? The search for extraterrestrial life has captivated our imagination for centuries, and thanks to assembly theory, we now have a new tool in this cosmic search. Assembly theory offers a unique approach to detecting extraterrestrial life. It is not about scanning the sky for radio signals or analyzing light spectra to detect the presence of oxygen, but it is about understanding the complexity of the molecules and structures that may indicate the presence of life. Let's imagine we scan the atmosphere of a distant exoplanet or the surface of a moon in our solar system. Using assembly theory, we could analyze the molecular complexity of the samples for patterns that indicate the presence of life. The higher the assembly index, the more likely it is that these molecules are the result of life and not random processes. However, the path to discovering extraterrestrial life is full of challenges and limitations. One of the biggest obstacles is our understanding of life itself. Our definition of life is based on what we know of life on Earth. What if it does not meet our biochemical standards? Another problem is the immensity of space. The universe is vast, and our ability to explore it is limited by current technology. Even with sophisticated telescopes and probes, we can only analyze a small fraction of the cosmos. In addition, assembly theory, although powerful, is still in its infancy. It's a new approach, and its application to the search for extraterrestrial life is uncharted territory. There are doubts about its applicability and accuracy in different environments, especially in those very different from terrestrial ones. Despite these problems, the potential of assembly theory in the search for extraterrestrial life is enormous. It could redefine our understanding of life in the universe and open new doors in astrobiology. Thus, assembly theory offers a new way of seeing life, not only as a biological phenomenon, but as an emergent property of cosmic complexity. Let's imagine the early days of our planet, a world in motion, a crucible for the chemistry of life. Here, in this chaotic environment, simple molecules began the journey of assembly, a process governed by physics and chemistry, but leading to something much deeper: life. According to assembly theory, life arises when these molecular structures reach a level of complexity that allows them to store and reproduce information. This is where chemical memory comes into play, a crucial step in the evolution of life. Chemical memory is the ability of certain molecular structures to conserve their structure. In other words, we can say that it is the blueprint of life in assembly theory. This is where reproducibility becomes key. The ability to reproduce these patterns, to transmit them from generation to generation, is what drives the evolution of life, from the simplest RNA molecules and the primordial soup to the great diversity of life we see today. Each step in this evolutionary journey has been a step forward in the assembly index. Each increase in complexity represents a triumph over the entropy that governs the universe. But the story of the origin and evolution of life is not only a story of increasing complexity, but also of resilience and adaptability. Life has found a way to thrive in the most extreme environments, from the depths of the ocean to the confines of space. In the realm of scientific discovery, each new theory is analyzed and debated. Assembly theory, a concept that promises to revolutionize our understanding of life and complexity, is now at a crossroads, questioned by critical voices such as Dr. Hector Zinal. The criticism presented by Zinal raises fundamental questions about the future evolution of assembly theory. Encompassing an impressive 18,000 words, the article requires time and reflection, and its dedicated reading can take between 1 and 2 hours. This is not a superficial review of the subject, but a deep immersion into the heart of the scientific debate. For those who are interested, we leave a link in the description to both articles, the study, and the counterarguments to it. Looking to the future, the role of the assembly theory in scientific research remains uncertain. Will it be able to adapt and overcome these challenges, or will it remain a footnote in the history of science? Despite the disagreements, one thing is clear. The debates around the assembly theory have started a conversation about the nature of scientific discovery and have highlighted the need for transparency, rigor, and humility in the pursuit of knowledge. In the end, the impact of assembly theory on future research may not lie in its specific claims, but in the lessons it teaches about the scientific process. As we explore the mysteries of life in the universe, these theories will come and go, but the search for understanding, the search to unravel the mysteries of our existence will always remain at the center of the interest of scientific research.